The universe as we know it began with a bang, literally. About 13.8 billion years ago, the Big Bang ignited the cosmos, sending matter and energy hurtling into an expansion that continues today. From this initial event, the first stars and galaxies began to form, marking the birth of everything we now recognize as the universe. But in the shadows of this creation, something far more mysterious was taking shape. Black holes. These enigmatic objects, initially theoretical concepts, became a cornerstone of modern astrophysics as scientists began to unravel their formation and nature. The formation of black holes is intricately tied to the birth of the first stars. In the earliest stages of the universe, gas clouds of hydrogen and helium began to collapse under their own gravity, forming the first generation of stars, known as population 3 stars. These stars were colossal, often much larger than those we see today, with masses up to hundreds of times that of our Sun. As they reached the end of their short-lived existence, these stars exploded in supernovae, leaving behind remnants so dense and compact that they became black holes. But how did these cosmic giants come to be, and why are they so significant in our understanding of the universe's infancy? One of the most compelling theories about the birth of black holes is that they form when massive stars reach the end of their life cycles and collapse under their own gravitational pull. The immense pressure and heat at the core of these dying stars cause nuclear fusion to cease, and gravity overwhelms the outward pressure of radiation. In an instant, the core contracts and the outer layers explode in a violent supernova, leaving a collapsed remnant, a singularity surrounded by an event horizon. This is the core of a black hole, an object so dense that nothing, not even light, can escape its gravitational pull. In these early moments, black holes were born out of Death Stars collapsing into oblivion to form some of the most fascinating objects in the universe. However, not all black holes form in this way. Theoretical models have suggested that primordial black holes could have formed in the incredibly dense conditions present just after the Big Bang. These black holes, unlike those created from stellar remnants, would have emerged from quantum fluctuations in the early universe. Imagine a region of space where the density was so high that gravity was strong enough to collapse matter into a singularity despite the absence of a star. These primordial black holes may have been the first seeds of darkness scattered across the cosmos, possibly serving as the building blocks for the larger black holes that would later grow by accumulating gas and other matter. Early observations of distant galaxies and the cosmic microwave background radiation hinted at the existence of these primordial black holes, but direct evidence remained elusive until the advent of more advanced telescopes. With the launch of the James Webb Space Telescope, JWST, we now have the technology to peer deeper into the past than ever before, observing galaxies that formed only a few 100 million years after the Big Bang. By studying these early galaxies, scientists hope to better understand the origins of black holes and whether primordial black holes played a crucial role in the formation of structures like supermassive black holes at the centers of galaxies, a significant breakthrough in black hole research has been the study of supermassive black holes, massive behemoths found at the centers of nearly every large galaxy, including our Milky Way. These supermassive black holes, whose masses can reach billions of times that of the Sun, likely formed from the accretion of matter in the early universe. Their formation is still a topic of intense research. Some theories suggest that these supermassive black holes may have grown by merging with smaller black holes or by accumulating enormous amounts of gas over time. The existence of such colossal black holes so early in the universe's history poses a challenge to current models of galaxy and black hole formation. How did these giant black holes form so quickly, and what was their connection to the galaxies around them? As we look deeper into ancient galaxies using cutting-edge instruments like the JWST, we find that the story of black holes is far from simple. Their birth, growth, and influence on the universe are far more complex and interconnected with the evolution of galaxies than previously imagined. The connection between black holes and galaxies is symbiotic. Galaxies provide the matter that black holes consume, while black holes exert a powerful influence on the development of their host galaxies. This feedback loop between black holes and galaxies could hold the key to understanding the true nature of black holes and how they evolve from the earliest moments of the universe. But what is it about black holes that captivates the imagination? The very idea of an object where gravity is so strong that not even light can escape challenges our understanding of the fundamental laws of physics. They push the boundaries of science and philosophy, offering a glimpse into the extremes of nature. They represent the unknown, a place where the fabric of space-time breaks down and reality as we know it ceases to apply. As our telescopes peer further into space, we continue to uncover new mysteries about black holes, unlocking the secrets of their birth, evolution, and their critical role in the universe's grand design. The phenomenon of dawn light. In the high darkness of the universe, black holes are often portrayed as the ultimate destroyers, devouring all light and matter that come too close. However, in the early universe, black holes cast a type of light that seems paradoxical, even magical, yet scientifically crucial to understanding the cosmos: the dawn light. This light, which emanates from black holes during their early formation, carries with it information about the universe's birth, information that in many ways is invisible to traditional telescopes. But how does light from black holes differ from the light we normally observe from stars, galaxies, or nebulae? The concept of dawn light revolves around the idea that although black holes are infamous for their ability to trap light within their event horizons, they also emit a form of radiation. This radiation, known as Hawking radiation, is theorized to be emitted by black holes due to quantum mechanical effects near the event horizon. However, the light we are most concerned with here is not so much about the black hole itself, but rather the intense activity around it. As matter falls into a black hole, it forms an accretion disk, a spiraling mass of gas, dust, and other material. This disk heats up to immense temperatures, radiating light across the electromagnetic spectrum. But this is not the ordinary starlight we're familiar with. It's a light that is heavily influenced by the black hole's gravity and the intense forces at play. In the early universe, these accretion disks would have been a source of immense brightness. As the first supermassive black holes began to form, they consumed enormous amounts of gas from their surroundings, causing their accretion disks to shine with unprecedented intensity. The light emitted by these disks was not only visible to distant observers, but also carried with it a unique spectral fingerprint that would allow scientists to discern the properties of the black hole and its surrounding environment, even from billions of light years away. But this light isn't like the steady glow of stars. While stars emit light through nuclear fusion, where hydrogen is converted into helium in their cores, black holes shine with an entirely different mechanism. As matter spirals inward, it is compressed and heated to extreme temperatures, producing X-rays and gamma rays. This process is a violent dance, with gravity compressing matter, causing it to glow intensely before it crosses the event horizon. The energy emitted by this process, often referred to as quasar light, becomes one of the brightest phenomena in the universe, outshining entire galaxies. This immense luminosity is often so strong that it can be observed even at vast distances. In essence, the light coming from early black holes is not just a simple emission of photons, it's a product of extreme physics in action. As matter is pulled into the black hole, it accelerates to relativistic speeds, generating powerful jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets, composed of highly energetic particles, emit radiation in a variety of wavelengths, from radio waves to X-rays, creating a spectacle that far exceeds the brightness of the galaxy. The light we see from these early black holes, specifically the quasars they form, is a cosmic beacon, providing insight into the very conditions of the universe's infancy. This light is crucial not only because it helps us observe the formation of black holes, but also because it serves as a tool for tracing the history of galaxy formation. The intense radiation from these early black holes influences the surrounding gas and matter, affecting how galaxies form and evolve. In many ways, the birth of black holes was inextricably linked to the birth of galaxies themselves. The light that we now observe from these early black holes is not only illuminating the black holes but also the cosmic environment in which they exist. By studying this light, astronomers can reconstruct the processes that took place billions of years ago. The first galaxies and black holes are contrast to the light we see from while stars emit light in a predictable, relatively stable fashion based on nuclear fusion occurring in their cores, black holes emit light in a far more chaotic and dynamic manner. The emission from black holes isn't steady, it flickers, pulses, and shifts. Sometimes the accretion disk can be obscured by surrounding matter, while other times the black hole's jets can produce flashes of light that vary in intensity. This dynamic nature of black hole light presents challenges for scientists who must decipher patterns in the radiation to understand the inner workings of these cosmic giants. Furthermore, the unique properties of black hole light, such as its polarization and redshift, offer clues about the physics around the event horizon, providing an indirect way to study the forces and matter that cannot be directly observed. As light travels through the curved space-time around the black hole, its path is distorted by the gravitational pull of the black hole, a phenomenon known as gravitational lensing. This bending of light allows us to observe distant objects that would otherwise be obscured, offering a glimpse into the farthest reaches of the universe. But this effect also allows us to study how light behaves near the edge of a black hole, shedding light on some of the universe's most fundamental questions about gravity, space, and time. As the JWST and other cutting-edge telescopes delve deeper into the universe, we are beginning to unlock the mysteries behind this dawn light. We are able to detect the faintest traces of radiation coming from early black holes, some of which formed only a few 100 million years after the Big Bang. This observation could hold the key to understanding the first stages of cosmic evolution, shedding light on how the first black holes and galaxies formed and how they influenced the development of the universe. Black holes and the formation of ancient galaxies. The story of galaxy formation is one that has captivated astronomers for decades. Traditionally, galaxies were thought to have formed through the gradual accumulation of gas and dust, which collapsed under gravity to create clusters of stars and stellar systems. However, as we peer deeper into the universe with advanced telescopes like the James Webb Space Telescope, JWST, a new chapter of galaxy formation is emerging, one where black holes play a central, active role in shaping galaxies from their very inception. In the early universe, black holes were not merely passive bystanders. They were driving forces in the creation of galaxies. Early supermassive black holes, those weighing millions or even billions of times the mass of our Sun, were born out of the intense gravitational collapse of gas clouds following the formation of the first stars. These primordial black holes grew quickly, feeding off vast clouds of gas and dust, and in doing so, they began to shape the galaxies around them. The black hole's gravity did not just pull in matter, it also exerted a profound influence on the surrounding environment, altering the dynamics of the entire galaxy. This process of galaxy formation was far more chaotic and intertwined with the existence of black holes than previously thought. Traditional models suggested that galaxies formed first and then, over time, black holes formed at their centers. However, emerging evidence suggests a far more symbiotic relationship. In the case of many of the earliest galaxies, the formation of a supermassive black hole at the center occurred almost simultaneously with the birth of the galaxy itself. These black holes served as engines of growth, powering the rapid assembly of galaxies by attracting surrounding matter and triggering bursts of star formation. The unique nature of these early black holes meant that they didn't just sit quietly. At the heart of galaxies, they actively influenced the development of stars. The accretion disks surrounding these black holes released massive amounts of energy in the form of radiation, which ionized the surrounding gas and affected the conditions in which stars could form. In some cases, black holes may have even suppressed star formation, by emitting intense radiation that heated up the gas surrounding them, preventing it from collapsing into new stars. Yet in other instances, the gravitational pull of the black hole could trigger the collapse of gas clouds, leading to bursts of star formation that helped build the galaxy. This interaction between black holes and star formation is what makes the early universe so fascinating. As the first galaxies formed, their growth was intrinsically linked to the behavior of the supermassive black holes at their centers. In some of the most massive galaxies, black holes likely grew rapidly, feeding off gas that spiraled in from the surrounding environment. This intense feeding frenzy, combined with the extreme energy emitted by the black holes, created some of the earliest quasars, blazing beacons of light that outshone their host galaxies. These quasars became some of the most powerful objects in the universe, emitting enormous amounts of radiation and helping to illuminate the cosmos during the cosmic dawn. By comparing the formation of ancient galaxies around black holes to traditional models, a stark contrast becomes apparent. The classic view of galaxy formation suggests a gradual, star-driven process where galaxies slowly accumulate matter and build up star systems over billions of years. In contrast, the black hole-driven model presents a far more dynamic and rapid process where the black hole not only feeds on gas, but also drives the growth of the galaxy through its radiation and gravitational influence. The presence of these black holes seems to have accelerated the formation of large-scale structures, triggering both the birth and death of stars at an unprecedented pace. The rapid growth of early black holes also raises important questions about the relationship between dark matter and galaxy formation. Dark matter, that invisible substance which makes up a significant portion of the universe's mass, plays a crucial role in the gravitational collapse of matter. Some theories suggest that black holes could have served as seeds around which dark matter gathered, influencing the formation of the dark matter halos that surround galaxies. These halos, which contain the majority of a galaxy's mass, may have been shaped and organized by the powerful gravitational forces of early black holes, helping to structure the entire galaxy. As we study galaxies that formed in the first few 100 million years after the Big Bang, we are gaining valuable insights into the role of black holes in shaping cosmic evolution. Telescopes like the JWST allow us to observe galaxies that formed just a few billion years after the universe's birth, shedding light on how black holes influenced galaxy formation during the universe's infancy. These observations suggest that the earliest black holes were crucial in the assembly of galaxies, and they may have played a key role in the development of the large-scale cosmic structures we see today. Observing dawn light through time. The light we see today is not just the light that exists in the present moment, it is a snapshot of the universe as it was in the past. Light, by its very nature, travels at a finite speed, meaning that when we observe distant objects, we are essentially looking backward in time. This concept is central to our understanding of the universe, especially when it comes to observing the earliest black holes and galaxies. As light from these ancient objects travels across the vast distances of the universe, it carries with it information about the conditions of the cosmos billions of years ago. With the advent of groundbreaking instruments like the James Webb Space Telescope, JWST, we now have the unprecedented ability to observe this ancient light in greater detail than ever before, offering us a window into the universe's infancy. When we gaze into the night sky, the stars we see are not the ones that currently exist as they are. The light reaching us from distant stars and galaxies may have left those objects millions or even billions of years ago. The farther away an object is, the older the light we see. In the case of early black holes, the light we observe today left these objects in a time when the universe was still in its formative stages, just a few 100 million years after the Big Bang. This means that when we peer at ancient galaxies or black holes through the JWST, we are not simply observing their present state, but instead catching a glimpse of them at a critical moment in cosmic history. The JWST is a game changer in this regard. Unlike its predecessors, the Hubble Space Telescope or ground-based observatories, JWST is equipped with an array of advanced instruments that allow it to observe the universe in infrared wavelength. These wavelengths are perfect for detecting the dawn light emitted by the first galaxies and black holes. Infrared light can travel through cosmic dust and gas that often obscures visible light, allowing JWST to peer deeper into the universe's past, beyond the reach of traditional optical telescopes. With its powerful infrared detectors, JWST can capture the faint signals emitted by ancient black holes, quasars, and the first galaxies that formed in the early universe. As light from these early black holes journeys across space, it becomes stretched out by the expansion of the universe. This phenomenon, known as redshift, causes the wavelengths of light from distant objects to lengthen as they travel toward us, shifting them into the infrared spectrum. The farther away an object is, the greater the redshift. This means that the light from early black holes, which may have originally been emitted in the visible or ultraviolet spectrum, is now observed as infrared light. JWST's ability to detect this red-shifted infrared light allows it to uncover the secrets of the earliest black holes and the galaxies they inhabit, enabling scientists to study them as they existed when the universe was only a fraction of its current age. But why is this light so important? The light from these early black holes is more than just a faint glow from distant objects. It holds the key to understanding the universe's early evolution. By studying this ancient light, we can trace the conditions that led to the formation of the first stars, galaxies, and supermassive black holes. We can learn how black holes grew in size, fed on gas, and interacted with their surrounding environment, shaping the galaxies they inhabited. This light also provides crucial insights into the nature of the universe during its infancy, such as the composition of the early universe, the presence of dark matter, and the processes that led to the formation of cosmic structures. The ability to observe light from black holes billions of years old is also a testament to the vastness of the universe. The light from these ancient objects has traveled across immense distances, crossing the vast expanse of space and time to reach us. Some of the black holes we observe today were formed just a few 100 million years after the Big Bang, during an era known as the Cosmic Dawn. During this time, the universe was still in the process of transitioning from an opaque, hot state to the clear, star-filled cosmos we see today. The light from these early black holes offers us a glimpse into this primordial era, allowing us to study the conditions that led to the formation of the first structures in the universe. As we observe this ancient light, we also uncover the mysteries surrounding the growth of supermassive black holes. How did these behemoths form so quickly after the Big Bang? What role did they play in the evolution of their host galaxies? By studying the light emitted by early black holes, scientists are beginning to answer these questions, gaining insight into the complex interplay between black holes, galaxies, and the broader cosmic environment. One of the most exciting aspects of observing dawn light through JWST is the potential to detect black holes in the process of formation. As light from these distant objects takes billions of years to reach us, we are effectively looking back in time to an era when black holes were just beginning to emerge from the primordial soup of the universe. This allows us to study the birth of these cosmic giants in unprecedented detail, offering a new perspective on the role they played in shaping the early universe. The mission of JWST, a new era in space observation, the launch of the James Webb Space Telescope, JWST, marks the dawn of a new era in space exploration and observation. For decades, humanity has relied on telescopes like Hubble and ground-based observatories to peer into the farthest reaches of the universe. However, despite their remarkable achievements, these instruments could only offer glimpses of the cosmos from a limited vantage point, primarily in the visible light spectrum. But now, with the JWST, we have a telescope capable of looking deeper into space and further back in time than ever before. With its powerful infrared technology, JWST can observe the universe in ways that were once considered impossible, unlocking secrets about distant black holes, ancient galaxies, and the birth of the cosmos itself. WST's ability to observe infrared light is its most defining feature and the key to its unprecedented capabilities. Unlike visible light, infrared light has longer wavelength and can travel through the cosmic dust and gas that often obscure our view of distant objects. In the early universe, when stars and galaxies were first forming, much of the light emitted by these objects was absorbed by surrounding gas and dust, making it invisible to traditional optical telescopes. JWST, however, is designed to capture this red light, allowing it to peer through these cosmic clouds and unveil the hidden structures of the early universe. Infrared observation is particularly critical when studying the first black holes and galaxies, as much of the light emitted by these objects has been stretched into the infrared spectrum due to the expansion of the universe, a phenomenon known as redshift. As light from distant objects travels across the vastness of space, it is gradually stretched out by the expanding universe. The farther an object is, the more its light is redshifted. This means that the light emitted by the first black holes and galaxies, which would have originally been in the ultraviolet or visible spectrum, is now observed as infrared light. By capturing this redshifted infrared radiation, JWST is able to look back in time to observe objects formed just a few 100 million years after the Big Bang. The ability to study these early objects in such detail is one of the most exciting aspects of the JWST mission. In particular, it is poised to revolutionize our understanding of the formation and evolution of black holes. In the first few 100 million years of the universe's existence, the first supermassive black holes began to form, rapidly growing in size by consuming vast amounts of gas and dust. These black holes, some of which may weigh billions of times the mass of the Sun, played a critical role in shaping the structure of galaxies and influencing star formation. However, despite their importance, the exact mechanisms behind their rapid growth remain a mystery. JWST's ability to observe infrared light from distant black holes will provide invaluable data on their formation and evolution. By studying the radiation emitted by the accretion disk surrounding these black holes, JWST can uncover the physical processes that drive their growth. The telescope's sensitivity to infrared wavelengths also allows it to detect faint emissions from early quasars, bright, energetic objects powered by supermassive black holes. Quasars are among the most powerful objects in the universe, and their light can outshine entire galaxies. By studying these distant quasars, JWST will help scientists understand how black holes grew so rapidly in the early universe and what role they played in the formation of galaxies. But JWST's capabilities extend far beyond the study of black holes. The telescope's infrared technology allows it to observe distant galaxies that formed in the wake of the Big Bang, offering a glimpse into the earliest stages of galaxy formation. As the universe expanded and cooled after the Big Bang, gas clouds began to collapse under gravity, giving birth to the first stars. Over time, these stars coalesced into galaxies, some of which would go on to host supermassive black holes at their centers. By observing these ancient galaxies in infrared wavelengths, JWST can provide new insights into how galaxies form, how stars were born, and how black holes shape their development. One of the most intriguing aspects of JWST is its ability to look further back in time than any telescope before it. Whereas Hubble could observe galaxies and black holes that formed roughly 400 million years after the Big Bang, JWST's infrared capabilities will allow it to study objects that formed just 100 to 200 million years after the Big Bang. This means that JWST will be able to capture the light from some of the very first galaxies and black holes, providing a direct look into the universe's early history. These observations will shed light on the cosmic dawn, a period when the first stars and galaxies emerged and the universe transitioned from a dark, opaque state to the clear, structured cosmos we see today. JWST's mission is not just about observing distant objects. It is also about studying the processes that govern the evolution of the universe. By observing the interaction between black holes, galaxies, and the gas that surrounds them, JWST will help scientists understand the complex relationships between these cosmic entities. It will also provide new insights into the nature of dark matter and dark energy, two of the most mysterious components of the universe that have eluded direct observation. As JWST peers into the early universe, it will uncover the role these unseen forces played in shaping the cosmos. The launch of JWST marks a significant milestone in humanity's quest to understand the universe. With its advanced infrared technology and unparalleled ability to observe distant objects, the telescope will open new windows into the past, revealing the secrets of black holes, galaxies, and the cosmos itself. As we begin to explore the early universe in unprecedented detail, we are on the verge of answering some of the most profound questions in science. How did the first black holes form? What triggered the birth of galaxies? And how did the universe evolve into the vast, complex structure we observe today? JWST will be our guide on this extraordinary journey, offering insights that will reshape our understanding of the cosmos for generations to come. JWST's capability to detect ancient galaxies. The James Webb Space Telescope, JWST, represents a monumental leap forward in our ability to study the ancient universe, particularly through its ability to detect light from galaxies that formed just a few 100 million years after the Big Bang. These early galaxies are crucial to understanding the universe's origins, the formation of the first stars, and the development of cosmic structures. Unlike its predecessor, JWST's advanced infrared capabilities allow it to see further back in time, capturing the faintest traces of light emitted by the first galaxy. But how exactly does JWST manage to peer into the distant past? And what does this ancient light reveal about the universe's infancy? To understand how JWST detects light from galaxies formed shortly after the Big Bang, we first need to consider the nature of light and the vast distances it must travel to reach us. Light from the most distant objects in the universe takes billions of years to reach us. Due to the expansion of the universe, the light emitted by these far-off galaxies has been stretched into longer wavelengths, a phenomenon known as redshift. The farther away a galaxy is, the more its light shifts toward the infrared part of the spectrum. This redshift makes it nearly impossible for traditional optical telescopes, such as the Hubble Space Telescope, to detect light from galaxies that formed early in the universe's history. However, JWST's advanced infrared sensors are specifically designed to capture this stretched, redshifted light, allowing it to see objects that are billions of years old. WST's capability to observe infrared light is key to its success in detecting ancient galaxies. Unlike visible light, which is often blocked by cosmic dust and gas, infrared light can pass through these obstructions. As a result, JWST can look beyond the thick clouds of gas and dust that often obscure our view of distant galaxies. This ability allows the telescope to observe galaxies that formed in the first few 100 million years after the Big Bang, during a period known as the Cosmic Dawn. This epoch marks the formation of the first stars and galaxies, an event that fundamentally changed the universe and paved the way for the development of more complex cosmic structures. One of the most powerful tools JWST uses to detect distant galaxies is its near-infrared camera, NER-CAM, which is capable of observing the universe in wavelengths ranging from 0.6 microns to 5 microns. These wavelengths correspond to the red and infrared portions of the spectrum, allowing JWST to detect the faint light from ancient galaxies that have been redshifted due to the expansion of the universe. By capturing this light, JWST can essentially look back in time, observing galaxies as they existed only a few 100 million years after the Big Bang. But how does JWST distinguish the light from distant galaxies from other sources? The answer lies in its ability to perform extremely precise spectroscopic measurement. Using its Integrated Science Instrument Module, ISIM, which houses its NIRCam and mid-infrared instrument, MIRI, JWST can separate the light from distant galaxies into its constituent wavelength. This process, known as spectroscopy, allows scientists to study the chemical composition, temperature, and motion of galaxies. By analyzing the spectral features of a galaxy's light, JWST can determine its redshift, revealing its distance and the time at which it formed. This technique is essential for studying the earliest galaxies, as it provides critical information about their age, size, and structure. WST's sensitivity to infrared light also enables it to observe some of the faintest objects in the universe. The light from early galaxies is extremely weak by the time it reaches Earth, having traveled across vast distances for billions of years. However, JWST's large, segmented primary mirror, capable of capturing more light than any previous space telescope, allows it to collect this faint light with unparalleled precision. The combination of this large mirror and the telescope's advanced infrared detectors allows JWST to observe galaxies that are up to 13.5 billion years old, or just a few hundred million years after the Big Bang. These observations of distant galaxies provide an invaluable glimpse into the conditions of the early universe. By studying the light from these galaxies, scientists can learn about the first stages of cosmic evolution, how the first stars ignited, how galaxies began to form, and how the universe transitioned from an opaque, hot state to the clear, structured cosmos we see today. JWST's ability to detect the light from these early galaxies also offers a window into the nature of dark matter and dark energy, two mysterious components of the universe that cannot be directly observed but are believed to play a crucial role in cosmic evolution. In addition to studying the formation of galaxies, JWST's observations will provide insights into how galaxies evolve over time. By comparing the properties of early galaxies to those of galaxies formed billions of years later, scientists can trace the processes that govern galaxy growth and evolution. For example, JWST will allow astronomers to study how the first galaxies merged to form larger structures, how supermassive black holes grew in the centers of these galaxies, and how star formation proceeded in the early universe. JWST's unprecedented ability to detect ancient galaxies and study their light will help answer some of the most profound questions in cosmology. How did the first galaxies form, and what did they look like? What were the conditions in the early universe that allowed galaxies to evolve? And how did the universe transition from a hot, featureless state to the vast, intricate cosmos? Unveiling the secrets of black holes with JWST, the James Webb Space Telescope, JWST, is transforming our understanding of the universe, offering an unprecedented view into the formation, structure, and evolution of black holes. These enigmatic objects, once seen as mere theoretical curiosities, are now recognized as central players in the cosmic drama. The ability of JWST to observe the universe in infrared wavelengths has opened new doors to studying black holes, particularly those formed in the early. Through its powerful infrared detectors, JWST is not only revealing the light emitted by black holes, but is also shedding light on their size, growth, and their profound influence on surrounding galaxies. One of the key ways JWST is unveiling the secrets of early black holes is through its ability to observe the light emitted by the hot, energetic material surrounding them. As gas and dust are pulled into a black hole, they form an accretion disk, a swirling, spinning mass of matter that heats up to incredible temperatures due to intense gravitational and frictional forces. This process generates enormous amounts of radiation, primarily in the form of X-rays and infrared light, as the material is compressed and heated before being pulled beyond the event horizon. JWST's ability to capture this infrared radiation is essential, as much of the light from distant early black holes has been redshifted into the infrared due to the expansion of the universe. By studying the infrared light emitted by the accretion disks around black holes, JWST can uncover critical details about their size and structure. The radiation from these disks provides a direct indication of the mass of the black hole and the rate at which it is consuming matter. The temperature and brightness of the accretion disk can also give clues about how quickly the black hole is growing. Supermassive black holes, which can have masses millions or even billions of times that of the Sun, are thought to have grown rapidly in the early universe. JWST's ability to detect this infrared radiation allows scientists to observe the growth of these cosmic giants, providing a deeper understanding of how they evolved so quickly after the Big Bang. In addition to studying the light emitted by the accretion disk, JWST can also observe the energetic jets of particles that many black holes emit. These jets, which are shot out from the poles of the black hole at nearly the speed of light, are another key signature of black hole activity. The exact mechanism behind the formation of these jets remains a topic of intense research, but they are believed to be the result of magnetic fields interacting with the accretion disk. As the material is drawn into the black hole, some of it is accelerated along the magnetic field line and ejected at high speeds, creating these powerful jets. JWST's infrared capabilities allow it to detect the faint radiation emitted by these jets, offering a unique opportunity to study their structure and composition. These observations are crucial for understanding how black holes influence their surrounding galaxies. Black holes are not just passive objects. They actively interact with their environments in a way that can affect the evolution of galaxies. The immense gravitational pull of a black hole can alter the motion of stars and gas within a galaxy, while the energy emitted by the accretion disk and jets can heat up the surrounding gas, potentially preventing new stars from forming. This feedback mechanism is thought to play a significant role in regulating the growth of galaxies, but the exact details of this process are still unclear. By studying the early black holes with JWST, scientists can gain insights into how these objects may have shaped the galaxies in which they reside. The light emitted by early black holes also provides valuable information about the conditions of the universe during its infancy. As the universe expanded and cooled after the Big Bang, the first black holes began to form, possibly as early as a few 100 million years after the cosmic dawn. These early black holes were likely much smaller than their modern counterpart, but they may have grown rapidly by accreting gas and merging with other black holes. JWST's ability to observe the light from these distant, early black holes allows scientists to study their formation and growth, providing a clearer picture of how these objects evolved and how they influenced their host galaxies. One of the most exciting prospects of JWST's observations is the potential to discover black holes that formed in the very first moments of the universe. These primordial black holes, if they exist, could offer valuable clues about the conditions of the early universe and the role black holes played in its evolution. While the search for primordial black holes is still ongoing, JWST's sensitivity to infrared light offers a unique opportunity to detect these elusive objects, shedding light on one of the most intriguing questions in cosmology: the echo of ancient light through space. The light emitted by ancient black holes is not merely a flash of brightness, it is an echo, a remnant of the universe's early days, traveling across vast stretches of space-time. When we observe this light today, we are looking at the past, glimpsing distant objects as they existed billions of years ago. This concept of cosmic echoes is central to our understanding of the early universe and the formation of black holes. Light from these distant objects emitted long ago has traveled across the cosmos, gradually losing energy as it spreads, yet still carrying with it crucial information about the conditions of the universe at the time. As this ancient light reaches us, telescopes like the James Webb Space Telescope, JWST, are uncovering these echoes, offering insights into the formation of the first black holes, galaxies, and the structure of the universe itself. The idea of cosmic echoes hinges on the fact that light, traveling at a finite speed, takes time to reach us from distant objects. When we observe a distant black hole or galaxy, we are seeing it as it existed in the past, not as it is now. The farther away an object is, the older the light we see. In the case of early black holes, the light we observe today left these objects billions of years ago, offering a glimpse into the universe's infancy shortly after the Big Bang. This is the essence of the echo, a faint but crucial trace, the distant past that is still reverberating across space-time. JWST, with its unparalleled infrared capabilities, is uniquely equipped to detect these cosmic echoes. The light emitted by ancient black holes, once visible in the ultraviolet and visible spectrum, has been stretched into longer wavelengths infrared due to the expansion of the universe. This phenomenon, known as redshift, causes the wavelength of light from distant objects to lengthen as they travel through the expanding space. The farther an object is from us, the greater the redshift, meaning that light from ancient black holes and galaxies has been stretched into the infrared part of the spectrum. JWST's sensitivity to infrared light allows it to capture this redshifted radiation, enabling it to observe the echoes of light emitted by the earliest black holes, formed just a few 100 million years after the Big Bang. But what can these cosmic echoes tell us? The light emitted by ancient black holes carries with it vital information about their formation, growth, and the environment in which they existed. As this light travels across vast distances, it undergoes several transformations. For example, the expansion of the universe causes the light to lose energy, shifting its wavelength and making it less intense by the time it reaches Earth. However, by analyzing the spectral characteristics of this ancient light, astronomers can uncover a wealth of information about the conditions of the early universe. They can determine the age, size, and growth rate of the black hole, as well as the nature of the materials surrounding it. This information is crucial for understanding how the first black holes formed and grew, and how they influenced the surrounding galaxy. In many ways, the theory of cosmic echoes is speculative. It is based on the assumption that light from the first black holes and galaxies has traveled across the universe, and that by observing this light, we can reconstruct the conditions of the early cosmos. While this theory has been a central part of cosmology for decades, it has remained largely hypothetical until now. With the launch of JWST, we now have the tools to detect these cosmic echoes in real time, providing direct evidence of the light emitted by ancient black holes. JWST's ability to observe distant galaxies and black holes in unprecedented detail is allowing us to test and refine these theories, turning what was once speculation into observable reality. The light from distant black holes provides not only a snapshot of the past, but also a guide to understanding the evolution of the universe. As the universe expanded and cooled after the Big Bang, the first black holes began to form, feeding on gas and dust and growing rapidly into supermassive objects. The radiation emitted by these black holes in the form of quasars and accretion. Disk light serves as a beacon that illuminates the surrounding regions of space. By studying the light from these ancient objects, JWST is allowing us to trace the growth and evolution of black holes and how they shaped the development of galaxies. One of the most exciting aspects of JWST's mission is its ability to observe black holes and galaxies that formed during the cosmic dawn, a period just a few 100 million years after the Big Bang. This epoch marked the formation of the first stars and galaxies, as well as the birth of supermassive black holes. By capturing the light from these early objects, JWST is revealing a previously unseen chapter of cosmic history. The echoes of light that JWST detects provide a direct connection to the origins of the universe, offering new insights into the processes that led to the formation of black holes and galaxies. Moreover, the study of these cosmic echoes is not limited to understanding the early universe. The light from distant black holes can also shed light on the fundamental nature of space and time. As light travels through the curved space-time around a black hole, it is distorted by the black hole's immense gravity, a phenomenon known as gravitational lensing. By studying how light is bent and stretched by these cosmic objects, scientists can gain new insights into the nature of gravity, the behavior of light near black holes, and the properties of space-time itself. This research has the potential to unlock some of the deepest mysteries of the universe. What are black holes and why do they matter? Black holes are among the most mysterious and fascinating objects in the universe. They have captivated the mind of scientists, philosophers, and the public alike for over a century, raising profound questions about the nature of space, time, and gravity. Once thought to be purely theoretical constructs, black holes are now considered essential components of the cosmos. But what exactly are black holes, and why do they hold such a central place in our understanding of the universe? To explore this, we must delve into the fundamentals of black hole theory, from their defining characteristics to their role in cosmology. At their core, black holes are regions of space where gravity is so strong that not even light can escape. This is the essence of what defines a black hole, an object with an incredibly dense core surrounded by a boundary called the event horizon. The event horizon marks the point beyond which nothing, not matter, nor light can escape the black hole gravitational pull. The surface of this horizon is not a physical surface in the traditional sense, rather, it represents the threshold where escape velocity exceeds the speed of light. Once something crosses the event horizon, it is trapped within the black hole's grasp, unable to return. The idea of a black hole emerged from Albert Einstein's theory of general relativity, which describes gravity as the curvature of space-time, caused by massive objects. According to Einstein's equations, if a massive star collapses under its own gravity at the end of its life, it can compress its matter into an infinitely small point, creating what is called a singularity. This singularity is surrounded by the event horizon, and it is the point where the laws of physics as we understand them break down. Beyond the event horizon, space-time becomes so warped that normal concepts of time and space cease to apply, making black holes some of the most extreme environments in the universe. Early theoretical predictions about black holes were met with skepticism. For decades, the idea of an object so dense that not even light could escape seemed almost absurd. It wasn't until the 1960s when physicists like John Wheeler and Roger Penrose further developed the mathematical framework of black hole theory that these strange objects began to gain traction in the scientific community. Around the same time, the discovery of quasars and other highly energetic cosmic phenomena gave indirect evidence for the existence of supermassive black holes at the centers of galaxies. Despite these advances, the nature of black holes remained speculative, with much of their internal structure and behavior still shrouded in mystery. In the decades that followed, black hole theory evolved dramatically. One of the key developments was the realization that black holes are not just theoretical oddities, they are integral to the functioning of the universe. The study of black holes has led to breakthroughs in many areas of astrophysics and cosmology, from the understanding of galaxy formation to the study of gravitational waves. For example, the discovery that most large galaxies, including our own Milky Way, contain supermassive black holes at their centers has transformed our view of galaxy evolution. These black holes play a crucial role in regulating the growth. Galaxies influencing everything from star formation to the structure of cosmic matter. Yet black holes continue to be objects of fascination because they challenge our understanding of the laws of physics. At the heart of a black hole lies the singularity, where matter is thought to be compressed to an infinitely small point, creating a region of infinite density. At this point, the equations of general relativity break down, and we are faced with a paradox. How can the laws of physics, which work so well in the rest of the universe, fail in such an extreme environment? This is one of the fundamental questions that has driven much of the research into black holes over the years. The event horizon itself also raises intriguing questions. While nothing can escape a black hole once it crosses the event horizon, we still have ways of observing the effects that black holes have on their surroundings. For example, the powerful jets of material ejected by black holes, known as relativistic jets, can be observed across vast distances, providing valuable information about the black hole's accretion disk and the material surrounding it. The radiation emitted from the accretion disk, particularly in the form of X-rays and gamma ray, provides indirect evidence of a black hole's presence, even though we cannot directly observe the black hole itself. In recent years, new breakthroughs have allowed scientists to study black holes in unprecedented detail. The Event Horizon Telescope, which captured the first ever image of a black hole's event horizon in 2019, marked a significant milestone in black hole research. This image, showing the shadow of a supermassive black hole at the center of the Galaxy M87, provided direct visual evidence of a black hole's existence and has spurred new investigations into the properties of these cosmic giants. Meanwhile, the detection of gravitational waves ripples in space-time caused by the collision of black holes has opened an entirely new window into black hole research, offering insights into their behavior and evolution. Perhaps the most compelling aspect of black holes is their ability to shape the universe around them. The intense gravitational pull of black holes influences everything from the formation of galaxies to the behavior of stars in their vicinity. In fact, black holes are thought to play a key role in the evolution of galaxies, regulating the amount of gas and dust available for star formation, and even triggering the formation of new stars in some cases. The interplay between black hole and galaxies is a subject of intense study, and understanding this relationship is crucial to understanding the large-scale structure of the universe. Today, the study of black holes is one of the most dynamic fields in modern astrophysics. While much progress has been made in understanding their nature and behavior, many questions remain unanswered. How do black holes form? What happens inside them? What is the true nature of the singularity at their core? These questions continue to challenge scientists, driving further exploration and discovery. Black holes remain enigmatic and awe-inspiring objects, their mysteries holding the key to understanding the deepest workings of the universe itself. Time warps and light bending around black holes. One of the most mind-bending aspects of black holes is their ability to warp space and time itself, creating a phenomenon so strange that it defies our everyday experiences of the universe. The immense gravitational pull of a black hole alters the fabric of space-time, bending it in ways that influence both the path of light and the flow of time. This extraordinary distortion, predicted by Albert Einstein's theory of general relativity, is most dramatically observed through two phenomena: gravitational lensing and time dilation. These effects not only shape our understanding of black holes, but also offer valuable clues about the universe's structure, especially when we look back at the earliest black holes formed in the wake of the Big Bang. To understand how black holes warp light, it's essential to first grasp the concept of space-time. In Einstein's framework, gravity isn't a force that acts at a distance, as was once proposed by Isaac Newton. Instead, it's a curvature of space-time itself, caused by the presence of mass and energy. When a massive object, like a black hole, is present, it bends the fabric of space-time in such a way that nearby objects, whether they're stars, galaxies, or light, follow curved paths. This warping of space-time creates a phenomenon known as gravitational lensing, which is one of the most visually striking consequences of black holes' influence. Gravitational lensing occurs when light from a distant object, such as a far-off galaxy, passes close to a massive black hole. As the light travels toward Earth, the black hole's immense gravity bends the light's path, magnifying and distorting the image of the distant object. The result is a warped, often ring-shaped appearance known as an Einstein ring. Gravitational lensing allows us to observe objects that would otherwise be hidden behind the black hole, acting as a natural telescope to magnify distant galaxies, stars, or even other black holes. The most famous example of gravitational lensing is the Hubble Space Telescope's observation of an Einstein ring in the galaxy cluster Hubble 2218, where light from galaxies behind the cluster was bent by its gravity. However, gravitational lensing isn't just a useful tool for studying the universe. It also provides a direct glimpse into the extreme nature of black holes. When we observe gravitational lensing, we're seeing the direct effects of a black hole's ability to distort space-time, offering us a glimpse into a phenomenon that would be otherwise invisible. The way light is bent around a black hole can reveal important information about its mass, size, and even its spin. By studying these distortions, scientists can indirectly map out the presence and properties of black holes that might otherwise be obscured. But gravitational lensing is just one aspect of how black holes influence light. Another key phenomenon related to black holes is time dilation, the warping of time itself. In areas of intense gravity, such as near a black hole, time behaves differently than it does in weaker gravitational field. The closer an object gets to a black hole, the slower time appears to pass, relative to an observer farther away. This effect, known as gravitational time dilation, is a direct consequence of the warping of space-time. As light moves toward a black hole, it's stretched not only in space but also in time, causing it to appear shifted toward longer wavelengths as it escapes. This means that from the perspective of a distant observer, light emitted from near a black hole's event horizon appears to slow down, eventually freezing at the event horizon itself. This warping of time is particularly dramatic near the event horizon of a black hole, the boundary beyond which nothing can escape. For an observer falling into a black hole, time would appear to pass normally from their own perspective. However, to an outside observer, time would seem to slow down as the falling object nears the event horizon, with the object's light becoming increasingly redshifted until it fades from view. The closer one gets to the black hole, the more pronounced this effect becomes, making the event horizon seem like a point of no return, both physically and temporally. The impact of time dilation on light is especially important when studying the earliest black holes in the universe. In the early stages of the universe's formation, the first supermassive black holes began to grow, consuming vast amounts of gas and forming powerful jets of material. The light emitted by these early black holes would have been dramatically affected by the warping of space and time as it passed near them. As JWST and other advanced telescopes observe light from these distant black holes, scientists must account for how this light has been stretched and altered by the black hole's immense gravity. Understanding how early black holes warped light and time can provide crucial insights into their growth, their relationship with the surrounding galaxies, and the fundamental physics that govern the universe. Moreover, the study of time dilation and gravitational lensing around black holes has important implications for our understanding of general relativity itself. The ability to observe how light bends and time slows down near black holes allows scientists to test the predictions of Einstein's theory in extreme conditions. These observations offer a unique laboratory for studying the limits of space-time, where the laws of physics are pushed to their breaking points. For example, gravitational lensing helps to confirm that space-time is curved as predicted by general relativity, and time dilation near black holes helps to validate the concept that time is relative, depending on one's position within a gravitational field. In the future, as telescopes like JWST continue to study black holes and their influence on light and time, we'll gain even more detailed insights into the nature of these cosmic objects. The ability to observe gravitational lensing and time dilation in real time will help us refine our understanding of the early universe, providing a clearer picture of how the first black holes formed, grew, and interacted with the galaxies around them. These phenomena remind us that black holes are not just mysterious void, they are dynamic, active objects that shape the very fabric of space and time, challenging our understanding of the universe at its deepest level, the shadow of a black hole and what it revealed. The idea of a black hole's shadow might sound paradoxical. How can something that doesn't emit light have a shadow? Yet, thanks to groundbreaking advancements in observational technology, particularly the Event Horizon Telescope, EHT, scientists have been able to capture the first ever images of a black hole's shadow. These images provide a unique glimpse into the nature of black holes and offer profound insights into their structure, behavior, and the surrounding space-time. But what exactly is a black hole's shadow, and what does it reveal about these enigmatic cosmic objects? A black hole's shadow is not a solid, physical feature, but rather the result of its extreme gravitational pull on light. As light from surrounding stars and gas gets caught in the black hole's gravitational field, it bends around the event horizon, the boundary beyond which nothing, not even light, can escape. This bending of light creates a region of darkness at the center of the black hole's image when viewed from a distance, forming what we refer to as the black hole's shadow. The shadow is essentially the outline of the event horizon, the point at which light is irrevocably trapped by the black hole's gravity. The Event Horizon Telescope, an international collaboration of radio observatories, achieved a historic milestone in 2019 when it captured the first image of a black hole's shadow. The black hole in question is located at the center of the galaxy M87, approximately 55 million light-years away from Earth. The image revealed a dark, circular shadow surrounded by a bright ring of glowing material, the accretion disk, showing us the intense environment around the black hole. This groundbreaking photograph confirmed several long-standing theoretical predictions about black holes, including the shape of their event horizons and the behavior of light near them. It was an extraordinary achievement in astrophysics, providing tangible evidence for the existence of black holes and opening the door to new ways of studying these objects. However, the black hole image captured by the EHT is not the only way to study black holes. The shadow itself holds crucial information about the black hole's size, shape, and spin. By analyzing the structure of the shadow and the surrounding light, scientists can determine the mass of the black hole and the orientation of its spin. The size of the shadow, for instance, is directly related to the black hole's mass. A more massive black hole will cast a larger shadow, while a smaller one will have a correspondingly smaller shadow. Similarly, the way the light around the shadow behaves can tell scientists about the black hole's spin. If the black hole is spinning rapidly, the light near the event horizon will be distorted in a characteristic way, revealing the black hole's rotational speed. In the context of the early universe, these observations provide a valuable comparison to theoretical predictions about the first black holes formed after the Big Bang. Black holes in the early universe were likely much smaller than those we see today, with masses only a few times that of the Sun. However, as time progressed, these early black holes could have merged and grown, eventually forming the supermassive black holes we observe at the centers of galaxies. The size and shape of these early black hole shadows would have been crucial for understanding their growth, and the first observations of such shadows would have provided an important benchmark for theoretical models of black hole formation. Interestingly, the black hole shadow seen in the M87 image also serves as a test of general relativity, Einstein's theory of gravity. The way light behaves near a black hole, especially as it is bent and distorted by the intense gravitational field, provides a natural laboratory for testing the predictions of relativity in extreme conditions. The Event Horizon Telescope's ability to measure and image the shadow with incredible precision allows scientists to compare these real-world observations with the predictions made by general relativity, confirming or challenging our understanding of space-time, gravity, and the very nature of black hole. While the shadow of M87's black hole is an extraordinary achievement, it represents only a small fraction of what's possible with future observation. The EHT continues to improve its resolution, and with advancements in telescope technology, we can expect to observe more black hole shadows in the near future. These images will likely provide further insights into the inner workings of black holes, particularly those formed in the early universe, which are essential to understanding the evolution of galaxies, stars, and cosmic structures. Moreover, as scientists continue to explore the relationship between black holes and the galaxies they inhabit, the study of black hole shadows can help illuminate the complex interplay between gravity, matter, and energy. By comparing the shadows of different black holes, especially those formed at various stages of the universe's evolution, we can trace the processes that led to the formation of supermassive black holes, the driving forces behind galaxy formation, and the fundamental physics that govern the cosmos. The shadow of a black hole, as captured by instruments like the Event Horizon Telescope, is not just a dark void in space, it is a key to understanding the very nature of these mysterious objects. These shadows reveal critical information about a black hole's size, mass, and spin, and by comparing them to theoretical predictions, they help scientists refine our understanding of the earliest black holes and their role in the universe. As technology advances, the shadow of a black hole will continue to be one of the most powerful tools in unlocking the mysteries of the cosmos. The role of black holes in shaping galaxies. Black holes, once thought to be cosmic oddities that simply consume everything in their path, are now understood to be integral players in the formation and evolution of galaxies. These enigmatic objects do more than just sit at the centers of galaxies. They actively shape the structure, dynamics, and evolution. Their immense gravitational pull and the powerful energy they emit influence the surrounding space, affecting everything from star formation to the distribution of matter in a galaxy. In this section, we will explore the ways in which black holes shape galaxies, focusing on their role in galactic formation and their ongoing interaction with galaxy structures. We'll also contrast theoretical models with observed phenomena, providing a clearer picture of the deep relationship between black holes and galaxies. One of the most striking discoveries in modern cosmology is that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center. These supermassive black holes, which can weigh millions or even billions of times the mass of the Sun, play a pivotal role in the dynamics of their galaxy. For many years, scientists believed that black holes formed only after galaxies did, but recent observations suggest a much more intertwined relationship between the two. In fact, black holes and galaxies may have formed simultaneously, with the growth of one influencing the other in a feedback loop that has shaped the structure of the universe as we know it. The process begins in the early universe, shortly after the Big Bang, when the first black holes began to form. These black holes were likely born from the collapse of massive stars or from the collapse of gas clouds in the dense early universe. As they formed, they began to grow by accreting material from their surroundings. This process of accretion is not a passive one. It releases enormous amounts of energy in the form of radiation, which affects the gas and dust in the galaxy. This energy can trigger or suppress star formation, depending on the amount of radiation emitted by the black hole. In some cases, the intense radiation from a black hole's accretion disk can heat up the surrounding gas, preventing it from collapsing into new stars. In other cases, the gravitational influence of the black hole can cause gas clouds to collapse, triggering a burst of star formation. This process, known as feedback, is one of the key ways in which black holes influence the evolution of galaxies. The energy released by a supermassive black hole can regulate the rate of star formation in its host galaxy, and this feedback mechanism plays a crucial role in the overall growth of the galaxy. Observations suggest that the size of a galaxy and the mass of its central black hole are closely correlated. In larger galaxies, supermassive black holes tend to be more massive, and these galaxies tend to have older, more evolved stellar populations. This correlation suggests that the growth of the galaxy and its central black hole are linked, with the black hole's energy output playing a role in regulating the galaxy's evolution. In addition to their role in star formation, black holes also play a crucial part in the overall structure of galaxies. The immense gravitational pull of a supermassive black hole helps to anchor the galaxy, keeping the stars, gas, and dust within the galaxy bound together. This gravitational influence affects the motion of stars and other objects in the galaxy, determining the overall shape and rotation of the galaxy. In spiral galaxies like the Milky Way, the black hole at the center helps maintain the galaxy's disk structure by influencing the dynamics of the surrounding stars and gas. The interaction between black holes and their host galaxies also extends to the formation of galaxy clusters. Supermassive black holes are thought to be responsible for the energetic jets of particles and radiation that are often observed in the centers of active galaxies. These jets, which can extend millions of light years from the black hole, can have a profound impact on the surrounding galaxy and even the larger galaxy cluster. The energy emitted by these jets can heat up the intergalactic medium, preventing the collapse of gas clouds into new galaxies and limiting the growth of galaxy clusters. In this way, black holes can influence the large-scale structure of the universe, shaping the distribution of galaxies across vast cosmic distances. However, while black holes are now understood to play a crucial role in galaxy formation and evolution, the exact nature of their influence remains a subject of intense research. Theoretical models suggest that black holes and galaxies form together in a kind of cosmic dance, with each influencing the growth of the other. Yet, observational evidence is still catching up to these theories. For example, the discovery of extremely massive black holes in very young galaxies challenges our understanding of how quickly black holes can form and grow. These observations suggest that black holes may have been much more influential in the early universe than previously thought, possibly helping to shape the first galaxies by regulating their growth. Theories about the role of black holes in galaxy evolution are further complicated by the ongoing mystery of how these supermassive objects form in the first place. While black holes in the early universe may have formed from the collapse of the first stars, it is unclear how these small black holes could have grown into the supermassive giants observed today. One possibility is that black holes in the early universe grew quickly by accreting large amounts of gas, while another theory suggests that they may have merged with other black holes to form larger objects. As telescopes like the James Webb Space Telescope, JWST, continue to observe distant galaxies, we may soon have the tools to uncover the precise mechanisms behind black hole formation and their role in shaping the earliest galaxies. Black holes are not just mysterious objects at the centers of galaxies. They are dynamic, active players in the cosmic drama, shaping the very structure and evolution of their host galaxy. From regulating star formation to influencing the overall structure of galaxies, black holes are integral to our understanding of the universe. The relationship between black holes and galaxies is one of feedback and interaction, where the growth of one influences the other in ways that continue to shape the universe's evolution. As we gather more observational data, especially with tools like JWST, we will continue to refine our understanding of how black holes and galaxies evolve together and how this symbiotic relationship has helped to shape the cosmos. The role of light in cosmic time travel. The concept of time travel, long a staple of science fiction, has always been tied to the ability to move backward or forward in time, experiencing moments from different eras. However, in the realm of astrophysics, we encounter a form of cosmic time travel that occurs naturally through the light that travels across vast stretches of space. Light, as it travels from distant galaxies and black holes, carries with it the history of the universe, offering us a glimpse into the past and allowing us to observe events that occurred billions of years ago. This phenomenon is a fundamental part of how we understand the flow of time in the cosmos. By studying the light that reaches us from the dawn of the universe, we are effectively looking back in time, traveling across cosmic history in a way that defies our usual experience of time. Light travels at a constant speed, approximately 299,792 kilometers per second, 186,282 miles per second, which, although incredibly fast, is finite. This means that when we look at distant objects in the universe, we are not seeing them as they are in the present moment. Instead, we are seeing them as they were when the light first left them, which could be millions or even billions of years ago. The farther away an object is, the older the light we see. For example, when we observe a distant galaxy or black hole, the light we see today may have left that object billions of years ago, giving us a direct view of how it appeared long in the past. This ability to look back in time through the light that reaches us is a crucial tool in unraveling the mysteries of the universe's history. This cosmic time travel is most striking when we observe the earliest galaxies and black holes form. After the Big Bang, the universe, as we know it, began about 13.8 billion years ago with the Big Bang, and since then, light has been traveling across the universe, spreading out and reaching us from ever more distant objects. The earliest galaxies formed only a few 100 million years after the Big Bang, and light from these ancient galaxies has been traveling across space ever since. Telescopes like the James Webb Space Telescope, JWST, are now enabling us to detect this ancient light, offering a glimpse into the first stages of cosmic evolution. When we observe this light, we are effectively peering into a time when the universe was still in its infancy, offering insights into the conditions that led to the formation of galaxies, stars, and black holes. One of the most fascinating aspects of observing light from distant galaxies and black holes is that this light is often redshifted. As light travels through the expanding universe, its wavelengths are stretched, causing it to shift toward the red end of the electromagnetic spectrum. This effect, known as cosmological redshift, is a direct consequence of the expansion of space itself. The farther away an object is, the more its light is stretched, shifting it to longer wavelength. For distant galaxies and black holes, this means that light originally emitted in the ultraviolet or visible spectrum is often observed in the infrared. This shift allows telescopes like JWST, which are designed to observe infrared light, to capture the light from the earliest galaxies and black holes that formed shortly after the Big Bang. By studying this redshifted light, scientists can not only observe distant objects but also determine their age, distance, and the time at which they formed. The implications of this ability to study light from the dawn of the universe are profound. It means that, in a sense, we can observe the very origins of the universe as though we are traveling back in time. Each photon of light that reaches us carries information about the state of the universe at the time it was emitted. By studying this light, scientists can learn about the conditions that existed in the early universe, such as the composition of the first galaxy, the process of star formation, and the growth of supermassive black holes. These observations allow us to trace the evolution of the universe from its hot, dense beginnings to the complex structure we see today, revealing the steps that led from the Big Bang to the formation of stars, galaxies, and planetary systems. Moreover, the study of light from distant black holes is particularly significant in understanding the nature of time itself. Black holes are regions where gravity is so intense that it warps space-time to an extreme degree. The light emitted from around black holes is affected by the warping of space-time, offering insights into how gravity influences the flow of time. As light approaches a black hole, it is stretched and redshifted due to the extreme curvature of space-time, and the closer the light gets to the event horizon, the point of no return, the more time seems to slow down. From the perspective of a distant observer, light near a black hole appears to freeze, providing a unique glimpse into the effects of gravity on the passage of time. By studying this light, scientists can test theories of general relativity and further explore the nature of space-time itself. We are not only learning about the past, but also about the fundamental forces that govern the universe. The light we see today is a direct connection to the past, offering a form of cosmic time travel that allows us to piece together the history of the cosmos. This light is a messenger from the past, carrying with it the stories of the universe's earliest moment. And as our telescopes improve, we will be able to observe even more distant objects, pushing further back in time and uncovering more of the universe's secrets. How light from black holes echoes through space. Light is not only the way we see the universe, it also serves as a time capsule, carrying with it the history of the cosmos. Light emitted by black holes, one of the most enigmatic phenomena in astrophysics, offers a unique glimpse into the past. But what happens when the light emitted by a black hole, which was once brilliant and intense, travels across space for billions of years? How does this light reach us, and how is it altered by the vast distances it traveled? The idea of light echoes presents an intriguing possibility that light emitted by black holes might still be detectable even after billions of years. In this section, we'll explore the theory of light echoes, how they can be studied, and how this concept contrasts with current methods for measuring cosmic distances and time. At the core of this idea is the understanding that light, like all forms of radiation, travels through space at a constant speed, the speed of light. However, as light journeys through the universe, it doesn't just travel in a straight line. It interacts with the space it moves through, encountering obstacles like cosmic dust, gas clouds, and gravitational fields, which can alter its path. For black holes, the interaction between light and the immense gravitational fields near them has a profound effect on how their light travels across space. The gravity of a black hole bends light and stretches its wavelength, often causing it to become redshifted. Additionally, the incredibly intense energy emitted by a black hole's accretion disk and surrounding jets can produce powerful flashes of light, some of which may remain visible long after the event that produced them. The concept of light echoes extends this idea further. When light from a black hole is emitted, it doesn't just travel away in a straight line indefinitely. Some of the light, especially if it is reflected or scattered by nearby matter, can travel along multiple paths, sometimes bouncing off objects like gas clouds, surrounding stars, or even cosmic dust. These interactions cause the light to reverberate, much like an echo that bounces off a wall and returns to the source. In the case of black holes, these echoes may reach Earth billions of years later, allowing us to detect light that was emitted long ago. This light, altered by its interactions with matter in space, carries with it information about the black hole and its environment, offering clues about how the black hole formed and how it interacted with its surrounding. One of the most exciting aspects of light echoes is that they allow us to observe cosmic events that occurred in the distant past. For example, when studying active galactic nuclei or quasars, the incredibly bright centers of galaxies that are powered by supermassive black holes, astronomers often detect a series of repeated signals or flashes of light. These signals, which arrive at slightly different times, are the result of light echoes. By carefully studying these echoes, scientists can infer details about the geometry of the black hole's accretion disk, the materials around the black hole, and how the light is bent and reflected across space. This technique provides a unique way to probe the structure and behavior of black holes, even when we cannot directly observe them. However, the phenomenon of light echoes is not without its challenges. The time it takes for light to travel across the vast distances of the universe is immense. Light from even the closest black holes can take millions of years to reach us, and from more distant black holes, it can take billions of years. This means that when we observe light echoes, we are essentially looking back in time, observing how the black hole appeared when the light was first emitted. This presents both an opportunity and a challenge. On the one hand, studying light echoes allows us to peer into the past and understand how black holes formed and evolved. On the other hand, the immense timescales involved make it difficult to directly link the light echoes to specific events in the life of the black hole. In contrast to light echoes, current methods of measuring cosmic distances and time rely heavily on the concept of redshift. Redshift occurs when light from distant objects is stretched as it travels through the expanding universe. This stretching of wavelengths provides a way for astronomers to determine the distance to far-off galaxies and black holes. The more redshifted the light, the farther away the object is. By measuring the redshift of light from distant black holes, scientists can estimate their distance from Earth and calculate when the light was emitted. This method, while incredibly useful for measuring large-scale cosmic distances, does not provide the same level of detail about the interactions between light and matter as light echoes do. In addition, light echoes present an opportunity to study the environment around a black hole in a way that redshift measurements cannot. By observing how light is scattered, bent, or reflected by nearby matter, astronomers can learn about the properties of the material surrounding the black hole. This material, known as the accretion disk, plays a crucial role in the growth of black holes and the energy they emit. Studying light echoes provides a more detailed picture of the accretion disk and the forces at work around the black hole, giving us insights into the processes that drive the most energetic events in the universe. The study of light echoes is still in its infancy, but it promises to provide a wealth of information about black holes, their surroundings, and their role in the evolution of galaxies. As our observational technology improves, particularly with the advent of advanced telescopes like the James Webb Space Telescope, JWST, we will be able to observe these echoes with greater precision and over longer time periods. This will allow us to refine our understanding of how light travels through space, how black holes interact with their environment, and how these interactions shape the evolution of the universe itself. The theory of light echoes offers a fascinating window into the past, allowing us to observe how light from black holes has traveled across space and time. These echoes not only help us study black holes and their accretion disk, but they also offer a new way to measure cosmic distance and understand the flow of time itself. Theoretical implication, time distortion, and time travel. The notion of time travel has long captured the human imagination, often portrayed as a fantastical journey to the past or future. But in the realm of theoretical physics, the concept of time travel is not merely a product of science fiction. It emerges from the equations of general relativity and the effects of extreme gravitational fields, particularly those near black holes. Time, as we experience it, is not an absolute constant. It can be warped, stretched, and distorted by the immense forces exerted by massive objects. Black holes, with their immense gravity, offer a fascinating example of time distortion, and they provide a theoretical backdrop for speculation about time travel. In this section, we'll explore how the distortion of time around black holes might offer the potential for time travel, contrasting speculative ideas with real-world examples of time distortion near massive objects. To begin, it's essential to understand how gravity influences time. According to Einstein's theory of general relativity, massive objects like stars, planets, and black holes cause space-time to curve. This curvature alters the flow of time, causing it to move more slowly in regions of stronger gravitational field. This effect, known as gravitational time dilation, has been experimentally confirmed near massive objects like Earth, where clocks at higher altitudes, weaker gravitational fields, run slightly faster than those at sea level. But near a black hole, the effects of time dilation become far more dramatic. As you approach a black hole, time itself begins to slow down relative to an outside observer. The closer you get to the black hole's event horizon, the boundary beyond, which nothing can escape, the more extreme this time dilation becomes. From the perspective of someone watching from a safe distance, an object falling toward a black hole would appear to slow down as it approached the event horizon, with time seeming to freeze at the horizon itself. In a sense, from this distant perspective, it would appear as if the object could never quite reach the event horizon. This phenomenon is a direct consequence of the warping of space-time near the black hole. Now let's explore the speculative implications of this time distortion for time travel. One of the most intriguing ideas is that, in theory, if you could survive the extreme conditions near a black hole, something that is not currently possible, it's conceivable that traveling through the black hole could result in a form of time travel. Theoretically, if a black hole could connect to another region of space-time, perhaps through a wormhole or another type of shortcut, traveling through the black hole could potentially allow an object or person to move through time, bypassing the usual constraints of linear time. This idea is often associated with what's called a wormhole, a theoretical structure that could connect distant parts of space and time. In the context of black hole, the concept of a wormhole suggests that a black hole might act as a passageway, not just through space but through time as well. If one could enter a wormhole, the thinking goes, they might be able to travel through time, emerging in a different era, either in the past or the future. While wormholes are consistent with the equations of general relativity, they remain speculative and have not been observed in nature. Additionally, the extreme conditions near a black hole make it highly unlikely that anything could survive the journey, let alone pass through a wormhole, which may itself be highly unstable. Contrast this theoretical possibility with real-world examples of time distortion that have been confirmed in much less extreme condition. For example, astronauts aboard the International Space Station, ISS, experience time differently than people on Earth. Due to the weaker gravitational field in orbit, time moves slightly faster for astronauts in space compared to those on Earth, as predicted by general relativity. This effect, however, is incredibly small, on the order of milliseconds per year. While this is a fascinating example of time distortion, it is far from the dramatic time travel portrayed in science fiction. In contrast, the time dilation near a black hole, where time could appear to almost stop, is orders of magnitude more extreme. Despite the speculative nature of time travel through black holes, time dilation remains one of the most fascinating aspects of studying these cosmic objects. Black holes stretch the fabric of space-time to such an extent that they create conditions in which time behaves differently than we experience on Earth. While the idea of using black holes for time travel remains firmly in the realm of theory, the extreme time dilation near them offers profound insights into the nature of space, time, and gravity. While current scientific understanding does not support the idea that we can travel through time in any practical sense, at least not through black holes, it does highlight how black holes serve as natural laboratories for studying the limits of our understanding of the universe. The way they bend light and distort time offers a glimpse into the deeper workings of space-time, where the familiar laws of physics break down in the face of extreme condition. Though time travel to the past or future may remain speculative, the exploration of time dilation near black holes has already provided a wealth of knowledge about the nature of time itself. The concept of time travel, influenced by light distortion and time dilation near black holes, remains a fascinating theoretical possibility. While current scientific methods and technology do not allow for time travel through black holes, the distortions in space-time near these objects offer a real, if dramatic, form of time travel in which time itself becomes a malleable, flexible concept. The potential for echoes in JWST's observation. The James Webb Space Telescope, JWST, is poised to revolutionize our understanding of the universe by unveiling some of its most ancient secrets. Among the most exciting possibilities is the potential to detect the echoes of ancient black holes light that has traveled vast distances over billions of years, offering a glimpse into the earliest moments of cosmic history. This concept of light echoes is not only a fascinating theoretical idea, but also one that could be realized through JWST's advanced observational capability. In this section, we will explore how JWST might uncover these cosmic echoes, comparing theoretical predictions with actual observations made by the telescope. The idea of light echoes is based on the principle that light, as it travels through space, can interact with various objects and phenomena, causing it to reflect or scatter before reaching us. In the case of black holes, especially those formed in the early universe, the light emitted from their accretion disks and surrounding environments may have been altered and redirected by intervening material. Over billions of years, this light could have bounced off gas clouds, other stars, or even the black hole's own accretion disk, creating an echo of the original emission. By studying these echoes, scientists can gain insight into the nature of the black hole, its formation, and the conditions of the early universe. One of the most significant ways JWST is capable of detecting these echoes is through its infrared capability. Unlike visible light, which is often blocked by cosmic dust, infrared light can travel through these obstructions, allowing JWST to peer deeper into space than ever before. The light emitted by early black holes would have been in the ultraviolet, or visible spectrum, but as it travels through space, the expansion of the universe causes it to become redshifted, shifting into longer wavelengths like infrared. JWST, equipped with sensitive infrared detectors, is ideally suited to capture this redshifted light, enabling it to detect the faintest traces of ancient black holes. The concept of echoes is particularly relevant when studying quasars, extremely bright objects powered by supermassive black holes at the centers of distant galaxies. When light from these quasars passes through surrounding gas clouds or other cosmic material, it can scatter and reflect, producing multiple echoes of the original light. These echoes provide important clues about the structure of the accretion disk, the nature of the gas surrounding the black hole, and the growth of the black hole itself. JWST's ability to study these echoes will allow scientists to measure the size, mass, and spin of ancient black holes with unprecedented precision, giving us a clearer picture of their role in the formation of galaxies and the universe's evolution. But while the theoretical possibility of detecting light echoes from ancient black holes is tantalizing, translating this theory into real observations is no easy feat. Detecting these echoes requires extremely sensitive instruments capable of capturing the faintest signals from the distant past. JWST's instruments, including its near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, are designed to detect the very weak, red-shifted light from distant objects, including those that formed only a few 100 million years after the Big Bang. By observing these early black holes, their light echoes, JWST could provide valuable data on how these objects formed and grew in the early universe. One challenge in detecting these echoes is the vast distance light must travel. Light from the earliest black holes has been traveling for billions of years, and by the time it reaches Earth, it has been stretched and weakened. As a result, the light we observe today is often faint and redshifted, making it difficult to detect with existing telescopes. However, JWST's powerful infrared capabilities allow it to gather this faint light with extraordinary sensitivity, potentially enabling it to detect echoes from black holes that were formed in the first few 100 million years of the universe's existence. Another challenge in studying light echoes is determining whether the observed signals are truly echoes or just background noise. Light from distant objects is often distorted by the intervening material between us and the object, such as cosmic dust or gas cloud. This can make it difficult to separate genuine echoes from other sources of light. JWST's ability to perform high-resolution spectroscopic measurements allows astronomers to distinguish between different types of light and isolate the echoes from black holes. By analyzing the spectral characteristics of the light, scientists can determine its origin, revealing whether it has been scattered, redshifted, or reflected by intervening material. The potential for detecting light echoes through JWST is not only a powerful tool for studying ancient black holes, but also offers a broader insight into the early universe. By analyzing the interactions between light and the material surrounding black holes, scientists can learn more about the conditions that existed in the early universe. For example, the presence of certain types of gas or dust could reveal information about the processes that led to the formation of black holes, stars, and galaxies. Additionally, studying the echoes of light can provide new insights into the role black holes played in shaping the evolution of galaxies, as well as the broader structure of the universe. The detection of light echoes from ancient black holes holds immense potential for unlocking the secrets of the early universe. JWST, with its advanced infrared technology and unparalleled sensitivity, is ideally positioned to detect these faint, redshifted signals and provide new insights into the formation and evolution of black holes. While the idea of light echoes has been primarily theoretical, the real-world observations made by JWST will help to bring this concept to life, offering a new window into the universe's past and expanding our understanding of the forces that shaped its evolution. As JWST continues to explore the distant universe, we may soon be able to peer into the echoes of the cosmos, unraveling the mysteries of black holes and the earliest moments of cosmic history. The heat, death of the universe, and black hole role. The concept of the heat death of the universe is one of the most chilling and fascinating theories in cosmology. It suggests that after an incredibly long period of time, the universe will reach a state of maximum entropy where all energy is evenly distributed and no usable energy remains to support processes like life, motion, or even the formation of new structure. In this cold, dark future, the universe will essentially grind to a halt. Black holes, those enigmatic cosmic giants, could play a significant role, in this ultimate fate. As the universe continues to expand, they may become some of the last remaining objects, slowly contributing to the overall state of heat death. To better understand how black holes fit into this theory, it's important to examine both their contribution to entropy and the ongoing expansion of the universe driven by dark energy. The heat death theory is grounded in the second law of thermodynamics, which states that entropy, the measure of disorder or randomness in a system, tends to increase over time. As the universe evolves, energy becomes more evenly distributed and stars burn through their fuel, eventually dying and leaving behind remnants, such as white dwarfs, neutron stars, and black holes. The long-term evolution of the universe, according to the heat death hypothesis, suggests that as stars burn out, galaxies drift apart, and matter becomes increasingly spread out. Over time, this process will lead to a state where all the matter in the universe is so spread out that no significant interactions, such as star formation or the creation of new structures, can take place. The universe will be left in a state of thermodynamic equilibrium, where everything is at the same temperature and no energy gradients exist to support processes that require energy flow. In this dark future, black holes could serve as the final remnants of the universe past. As these massive objects continue to grow by accreting gas, dust, and even stars, they could become some of the last active structures in the universe. However, even black holes are not immune to the inevitable march toward heat death. According to physicist Stephen Hawking's groundbreaking theory of Hawking radiation, black holes are not entirely black. Over incredibly long periods of time, they slowly emit radiation due to quantum effects near the event horizon. This process, though extremely slow for large black holes, results in the eventual evaporation of the black hole. As black holes lose mass through this radiation, they gradually shrink and fade away, contributing to the overall increase in entropy in the universe. This slow process of evaporation is often referred to as the end of the black hole, or black hole death, and it will continue until the black hole is completely gone. The evaporation of black holes is a key component in the transition to the heat death of the universe. As black holes lose mass and energy through Hawking radiation, they increase the total entropy of the universe, pushing it toward a state of maximal disorder. Even as black holes fade, they still contribute to the cosmic heat death by dispersing energy in the form of radiation. In a universe where stars no longer shine and matter is nearly evenly distributed, the evaporation of black holes will mark the final stages of cosmic evolution, leaving behind a universe where entropy reigns supreme, with no further events or processes to occur. However, the heat death theory does not occur in isolation. The universe's continued expansion, driven by dark energy, plays a crucial role in how the universe will reach this ultimate fate. Dark energy, the mysterious force that is causing the accelerated expansion of the universe, works against gravity and pushes galaxies apart. Over time, this expansion will continue to accelerate, causing galaxies to drift farther and farther away from one another. As this happens, the universe's overall density decreases, making it harder for stars to form or for matter to interact meaningfully. The expansion driven by dark energy also means that black holes, stars, and galaxies will become increasingly isolated, further contributing to the entropy of the universe. Dark energy's role in the heat death theory is crucial because it accelerates the process by which the universe reaches thermodynamic equilibrium. As galaxies drift farther apart and as black holes slowly evaporate, the universe will enter a period of extreme isolation. This scenario is the ultimate expression of the second law of thermodynamics, a universe in which all energy is spread evenly and no meaningful work can be done. There will be no more interactions between particles, no more star formation, and no more complexity. The universe will exist in a state where there is no longer any distinction between hot and cold, dense and diffuse. All regions will be essentially the same. In contrast to the heat death theory, some theories of cosmology focus on the expansion of the universe in terms of the potential for new structures to form. Some have speculated that dark energy could lead to scenarios in which the universe expands infinitely, creating a big rip that tears apart galaxies, stars, and even atoms. However, the heat death theory doesn't involve such dramatic destruction. Instead, it envisions a universe in which all processes cease over time, and all that remains are cold, lifeless remnants like black holes slowly evaporating into nothing. The role of black holes in the heat death of the universe highlights their paradoxical nature. While they are among the most active and powerful objects in the universe, their eventual demise through Hawking radiation serves as a quiet, inevitable step toward the universe's final state. Black holes are, in a sense, the universe's last gasp, the final stage in the universe's transition from a vibrant, evolving entity to a lifeless, stagnant state. The heat death theory presents a chilling but fascinating vision of the universe's ultimate fate. Black holes, though active and energetic in their lifetimes, play an essential role in this eventual cosmic conclusion, contributing to the entropy of the universe as they slowly evaporate. Coupled with the ongoing expansion driven by dark energy, the heat death scenario underscores the inevitability of a universe in which all energy is spread uniformly and no further events can unfold. While this theory remains one of the most widely accepted models for the long-term future of the universe, it also invites questions about the nature of time, entropy, and the ultimate fate of all cosmic structures, including black holes themselves. Black holes as final witnesses of the universe's death. As the universe continues to evolve, both in time and space, the ultimate fate of everything within it remains an enigmatic subject of speculation. One particularly haunting possibility is that black holes, those dense, gravitationally intense objects, will be the last remaining structures in the universe. As galaxies drift apart, stars burn out, and matter disperses across the vast expanse. Black holes may continue to exist long after all other forms of cosmic life have faded away. In this sense, black holes could become the final witnesses to the universe's slow death, enduring the last vestiges of the cosmos before they themselves vanish. This section explores this idea, examining how black holes might serve as the final remnants of the universe's demise, and contrasts this scenario with theories that posit cosmic rebirth and the possibility of cyclic universes. Black holes, with their immense gravity, are the ultimate cosmic survivors. As stars exhaust their nuclear fuel and galaxies lose their gas, the rate of new star formation will gradually decline. In the far future, the universe will be dominated by remnants of stars and galaxies, white dwarfs, neutron stars, and of course, black holes. Unlike stars, which burn out and fade away, black holes can endure for vast amounts of time. Even as the universe continues to expand, black holes will continue to exist, slowly consuming the surrounding matter. As their environments grow colder and emptier, black holes may become the last structures in the universe, remaining as silent witnesses to the cosmic events that unfolded over billions of years. In this distant future, the universe will have reached a state of thermodynamic equilibrium. Entropy, the measure of disorder, will have increased to the maximum level, leaving no gradients of energy to drive physical processing. Stars will no longer shine, galaxies will be spread across an ever-expanding void, and even the most stable remnants of cosmic life, black holes themselves, will begin to evaporate. Through a process known as Hawking radiation, theorized by physicist Stephen Hawking, black holes gradually lose mass over time, emitting radiation due to quantum mechanical effects near their event horizons. This slow evaporation process, which can take longer than the current age of the universe for supermassive black holes, eventually leads to the demise of even these cosmic giants. However, this process is extraordinarily slow, and for all practical purposes, black holes will outlast everything else in the universe. As black holes slowly lose mass and energy, they will leave behind only a faint trace of their former selves, contributing to the entropy of the universe. These final moments in which black holes gradually fade into nothingness could mark the end of the universe itself, as all matter and energy reach a state of maximum entropy. In this scenario, black holes would be the ultimate witnesses to the death of the universe, a cold, dark, and still place where no new life or events can occur, and where nothing of any significance ever takes place. The last photons emitted by black holes as they evaporate will serve as the final remnants of the universe's once vibrant existence, echoing across an increasingly empty and featureless cosmos. However, the idea that black holes will simply fade away into a quiet end is not the only theory for the universe's final fate. There are alternative cosmological models that envision a more dynamic conclusion, one in which the universe may undergo cycles of rebirth. The cyclic model of the universe suggests that the cosmos might go through infinite cycles of birth, evolution, and death. According to this theory, the universe undergoes a big bounce, in which it contracts and then re-expands after reaching a point of maximum compression. This model contrasts sharply with the heat death scenario, where the universe simply fades into a lifeless, cold state. In a cyclic universe, black holes could play a different role. Rather than serving as the final witnesses to the universe's death, they might be part of a cosmic recycling process. The idea is that black holes could act as conduits between different phases of the universe, with their interiors potentially leading to new regions of space-time where the next cosmic cycle begins. In this scenario, black holes are not just final remnants, but active participants in an eternal process of cosmic rebirth. The matter and energy that fall into black holes could be redistributed, either through quantum processes or by connecting to another part of space-time, facilitating the creation of new stars, galaxies, and potentially a new universe. This idea of a cyclical universe is consistent with the theory of eternal inflation, which proposes that the universe continually expands, with new regions of space-time constantly being created. In this view, black holes may not mark the end of the universe, but rather represent the collapse points where new universes might emerge. Each collapse could create conditions for a fresh universe, continuing the cycle of cosmic birth and death indefinitely. In this model, black holes are not the final witnesses of the universe's death. Rather, they are gateways to new beginnings. The contrast between the heat death of the universe and the cyclic universe model highlights the uncertainty of cosmology's long-term prediction. While the heat death scenario suggests a universe that ends in a quiet, uniform state of maximum entropy, the cyclic model envisions a universe that continually renews itself, where black holes play a role in perpetuating cosmic life. Both theories highlight the centrality of black holes in understanding the universe's evolution, but they offer radically different conclusions about the ultimate fate of the cosmos. Black holes are poised to be the final witnesses to the universe's death, surviving long after the stars burn out and galaxies drift apart. Their slow evaporation through Hawking radiation will mark the final stage of the universe's journey toward maximum entropy, leaving behind only traces of their existence. However, alternative theories, such as the cyclic universe model, suggest that black holes might serve as conduits for the birth of new universes, offering the possibility of cosmic rebirth rather than an eternal end. These contrasting views underscore the fundamental mysteries of the universe and our understanding of time, life, and the ultimate fate of all things. How JWST could uncover the universe's fate. The James Webb Space Telescope, JWST, represents a major leap forward in our ability to observe the distant universe, offering unprecedented insights into the earliest moments of cosmic history. Particularly, its capacity to observe black holes and their interactions with surrounding galaxies could shed light on how these cosmic giants influence the large-scale evolution of the cosmos. In this section, we will speculate on how JWST's observations might contribute to our understanding of the universe's long-term destiny, focusing on black hole activity and their profound impact on galactic evolution. One of the most significant contributions JWST can make in understanding the universe's fate is through its observations of supermassive black holes. These black holes, found at the centers of most large galaxies, including our own Milky Way, are not just passive structures but active participants in the cosmic drama. Supermassive black holes are believed to have a symbiotic relationship with their host galaxy. Their growth and activity can profoundly affect the galaxies around them, influencing everything from star formation rates to the overall structure of the galaxy. By studying how these black holes interact with their environment, JWST can offer critical insights into how black holes could contribute to the ultimate fate of the universe. JWST's infrared capabilities will allow scientists to observe the early stages of black hole growth, offering a glimpse into how they shaped the first galaxies that formed after the Big Bang. In the early universe, black holes grew rapidly by accreting vast amounts of gas, and the energy emitted by these accretion disks powered some of the brightest objects in the universe, quasars. These quasars were the cosmic beacons of the early universe, emitting intense radiation that influenced the gas surrounding them, which in turn affected the formation of stars and galaxies. By studying these quasars in greater detail, JWST can provide insights into how the first supermassive black holes formed, how quickly they grew, and how their energy affected the evolution of the galaxies they resided in. This understanding of black hole activity is crucial for grasping the broader trajectory of the universe. Supermassive black holes are thought to play a central role in the regulation of galaxy growth. The energy emitted by a black hole can inhibit or stimulate star formation, a process known as feedback. In some galaxies, the intense radiation from a black hole's accretion disk may prevent gas from cooling and condensing, thus suppressing star formation. In others, the gravitational and energetic influence of a black hole might trigger the collapse of gas clouds, leading to a burst of new stars. As JWST probes these processes, it could help clarify how black holes contribute to the evolution of galaxies and whether they have a hand in the eventual fate of cosmic structures. JWST's observations could also provide insights into how black holes evolve over time and how their interactions with galaxies evolve as well. In the distant future, as the universe continues to expand, black holes might play an increasingly important role in the universe's fate. As galaxies drift apart and matter becomes more diffuse, black holes could become some of the last active objects in the universe, serving as the final remnants of the cosmos. Through its infrared observations, JWST could monitor the slow evaporation of black holes via Hawking radiation, offering a glimpse into how these objects slowly lose mass and energy. This slow fade of black holes could mark the final stages of cosmic evolution as the universe moves toward a state of maximum entropy, a concept known as the heat death of the universe. Additionally, JWST's ability to detect faint signals from the early universe allows scientists to study the expansion of the universe. By observing the redshift of light from distant galaxies, JWST will help us measure the rate of expansion and the role of dark energy, the mysterious force that accelerates the expansion of the universe. Understanding how dark energy influences the universe's expansion is crucial for predicting its ultimate fate. If dark energy continues to accelerate the universe's expansion indefinitely, the cosmos may end in a cold, dark, and isolated state, with galaxies and stars too far apart for any meaningful interaction. Moreover, JWST will play a key role in bridging the gap between theory and observation. Much of our understanding of the universe's fate, whether it is a slow fade into a state of equilibrium or a dramatic rebirth through cyclic processes, remains speculative. JWST's observations will test various cosmological models, offering concrete data on how galaxies, stars, and black holes interact on the largest scales. As it reveals the nature of the early universe and the evolution of its most massive object, JWST will help us refine our theories about the universe's future, providing new insights into the forces shaping its destiny. JWST has the potential to significantly advance our understanding of the universe's fate by studying the behavior of black holes and their impact on the evolution of galaxies. Through its observations of the early universe and black hole activity, the telescope could help us unravel the cosmic processes that determine the ultimate end of the universe. Whether through the study of supermassive black holes, galaxy evolution, or the role of dark energy, JWST promises to offer critical insights into the future of our universe, guiding our understanding of the forces that will shape its final days. Black holes, time, and the infinite cycle of the cosmos. Black holes have long been enigmatic cosmic entities, not only for their immense gravitational pull, but for their potential to unlock some of the deepest mysteries of space-time. Over the centuries, scientists have theorized about the possibility that black holes may not simply be dead ends for matter and energy, but could, in fact, serve as gateways to parallel universes or be integral parts of a cyclical universe model. This speculative idea raises fascinating questions about the nature of time, the fabric of space-time, and the universe's ultimate fate. In this section, we'll explore the hypothesis that black holes might be keys to understanding an infinite cycle of cosmic rebirth, contrasting this notion with our current understanding of cosmology and examining how the findings from JWST could revolutionize our perspective on these ideas. One of the most tantalizing theories about black holes involves the idea that they might serve as gateways to parallel universes. This concept finds its roots in the notion of the multiverse, which posits that our universe is not the only one. Instead, there could be an infinite number of universes, each with its own laws of physics, constants, and structures. Black holes, with their intense gravitational fields and mysterious singularities, may offer a means of connecting different regions of space-time or even different universes. This idea is not just the stuff of science fiction. It has roots in theoretical physics, particularly in the study of wormholes and Einstein-Rosen bridges. These theoretical structures suggest that black holes might act as tunnels or shortcuts through space-time, linking distant parts of the same universe or potentially connecting to entirely separate universes. The idea that black holes could be portals to parallel universes is grounded in the framework of general relativity and quantum mechanics, two pillars of modern physics. According to general relativity, black holes represent regions of space where the curvature of space-time becomes infinitely steep. If a wormhole exists within a black hole, it might provide a bridge between different regions of space-time or even different universes. Quantum mechanics, which governs the behavior of subatomic particles, also suggests that quantum fluctuations could give rise to multiple universes with different physical properties. The extreme conditions inside black holes, where both general relativity and quantum mechanics must be considered together, may provide a natural environment for such phenomena to occur. However, the possibility of black holes being gateways to parallel universes remains speculative. While theoretical models support this idea, it's important to note that no empirical evidence has yet been found to confirm the existence of wormhole or parallel universe. The extreme environments near black holes make them difficult to study directly, and the limits of current observational technology leave us largely in the realm of speculation. That said, the launch of the James Webb Space Telescope, JWST, has the potential to change this perspective. With its powerful infrared capability, JWST could provide us with new data on the most distant regions of the universe, enabling us to study galaxies and black holes that formed only a few 100 million years after the Big Bang. These observations could offer indirect evidence about the properties of black hole, their role in galactic formation, and whether there is any hint of phenomena like wormholes or quantum anomalies near black holes. Another compelling concept that JWST could help us explore is the idea of a cyclic universe, a model in which the universe undergoes an eternal cycle of birth, evolution, and death. In this model, black holes might serve not only as cosmic endpoints, but also as key players in the universe's regeneration. Instead of the universe expanding forever or collapsing into a single point, as in the heat-death scenario, a cyclic model posits that after each cycle the universe could bounce, potentially starting a new phase of cosmic evolution. In such a scenario, black holes might act as the bridges that facilitate the rebirth of the universe, with matter and energy sucked into them during the contraction phase and later released to fuel a new cosmos. The idea of a cyclical universe is informed by theories such as eternal inflation, which suggests that after the Big Bang, the universe went through rapid periods of expansion. If this inflationary process were to repeat indefinitely, it could give rise to new universes within the same framework. In this sense, black holes might be more than just the remnants of the old universe, but active conduits that help to transition the universe from one cycle to the next. However, like the idea of black holes as gateways to parallel universes, the cyclic model remains theoretical, with no direct observational evidence to confirm it. Our current understanding of cosmology, which largely revolves around the concepts of dark energy and the expanding universe, presents a stark contrast to the idea of a cyclical universe. The accelerating expansion of the universe, driven by dark energy, suggests that the universe will continue to expand forever, gradually losing energy and heading toward the ultimate state of thermodynamic equilibrium, or heat death. According to this model, black holes, along with all other forms of matter, will eventually fade away, and the universe will enter an eternal, lifeless state. Yet, as we explore these ideas, JWST's observations may provide new clues that challenge our understanding. By peering deeper into the distant universe than ever before, JWST could detect the earliest stages of galaxy and black hole formation, revealing patterns that might suggest a more cyclical nature to cosmic evolution. Moreover, its ability to study the cosmic background radiation and measure the behavior of dark energy could lead to new insights about the long-term fate of the universe, possibly offering evidence that revises our current models of cosmic expansion and entropy. Black holes, with their mysterious nature and immense gravitational pull, could play a fundamental role in the universe's ultimate fate, whether as gateways to parallel universes or key components in a cyclical model of cosmic evolution. These objects continue to fascinate and challenge our understanding of space and time. JWST's observations, with its powerful tools and capabilities, might provide the data needed to either confirm or revise these speculative ideas, helping us to better understand the true nature of the universe and the role black holes play in its destiny. The ultimate fate of the cosmos, whether it be an eternal death or a continuous cycle of rebirth, could be within our grasp, with JWST serving as our window to the farthest reaches of cosmic history. The quest for understanding the unknown. Quest to understand the cosmos is a journey that spans centuries of human curiosity and scientific discovery. From the ancient philosophers gazing at the stars to the cutting-edge technologies of today, humanity has always sought to answer fundamental questions about the nature of the universe. How did it begin? What lies beyond the observable? How do the forces of nature shape the cosmos? With the advent of telescopes and space missions, our understanding of the universe has evolved in ways that were once unimaginable. However, even with the remarkable achievements of instruments like the James Webb Space Telescope, JWST, the journey is far from over. In this section, we will explore the ongoing quest to understand the unknown, focusing on the groundbreaking discoveries made by JWST and contrasting them with the possibilities for future technologies and missions that may help us reach the next frontier of cosmic exploration. The launch of the James Webb Space Telescope in December 2021 marked a new era in space exploration, providing us with unprecedented views of the universe. JWST's ability to observe the cosmos in infrared wavelengths has allowed scientists to peer into regions of space that were previously hidden from view, from the formation of the first galaxy to the inner workings of black hole. By observing distant galaxies and black holes, JWST has already begun to shed light on some of the most profound mysteries of the cosmos, including the nature of dark matter and dark energy, the birth of stars and galaxies, and the evolution of supermassive black holes. One of the most remarkable discoveries of JWST has been its ability to observe the early universe, specifically galaxies that formed just a few 100 million years after the Big Bang. These observations have provided valuable insights into the processes that led to the formation of galaxies and stars, offering clues about how the universe evolved from a hot, dense state to the vast, structured cosmos we see today. JWST's ability to detect the faintest traces of light from these ancient galaxies has helped us push back the boundaries of our knowledge, revealing a more detailed picture of the universe's infancy. But while JWST has already made incredible strides, it is only the beginning of the cosmic exploration that lies ahead. The future of space exploration holds even more exciting possibilities as new technologies and missions are being developed to push the limits of what we can observe and understand about the universe. The next generation of telescopes and space missions will continue to build on the foundation laid by JWST, exploring uncharted territories of space and time and helping us answer questions that have long eluded us. One of the key missions that will follow in JWST's footsteps is the Nancy Grace Roman Space Telescope, formerly known as JWST, which is expected to launch in the mid-2020s. This mission will focus on studying dark energy and dark matter, two of the most mysterious components of the universe. By measuring the expansion of the universe and observing the distribution of galaxies, Roman will provide crucial data on the nature of dark energy, which is thought to be responsible for the accelerated expansion of the cosmos. Roman will complement JWST's observations by providing wide-field imaging and spectroscopic capabilities, offering a broader view of the universe and enhancing our understanding of the cosmos on the largest scales. Looking further into the future, there are plans for even more ambitious missions such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT. These ground-based telescopes currently under construction will be capable of observing the universe with unmatched clarity, thanks to their enormous mirrors up to 40 meters in diameter. ELT and TMT will provide unparalleled resolution, allowing scientists to study the atmospheres of exoplanets in unprecedented detail and search for signs of life beyond our solar system. These observatories will play a crucial role in advancing our understanding of the conditions required for life to exist and the potential for habitable worlds in other star systems. Additionally, future space missions such as the LUVOIR, Large UV Optical IR Surveyor, and HABEC, Habitable Exoplanet Observatory, are being designed to directly image exoplanets, providing a closer look at their atmospheres and potentially discovering biomarkers that could indicate the presence of life. These missions will further expand our ability to search for habitable worlds beyond our own, a pursuit that has captivated the scientific community for decades. While these missions represent the next steps in our quest to understand the universe, they also highlight the limitations of current technology. Despite the groundbreaking discoveries made by JWST, many fundamental questions remain unanswered. For example, while we have a general understanding of how galaxies form and evolve, we still don't fully understand the mechanisms behind the formation of supermassive black holes. The nature of dark matter and dark energy also remains elusive, with scientists still trying to identify the underlying particles or forces responsible for these phenomena. Additionally, while JWST has given us a glimpse into the early universe, there are still many unanswered questions about the first few moments after the Big Bang, questions that future missions will need to address. As we look to the future, the goal is not just to observe the universe, but to better understand its underlying principles, how it works, how it evolved, and where it is headed. Technologies such as gravitational wave observatories, like the Laser Interferometer Space Antenna, LISA, will allow us to study the ripples in space-time caused by massive objects like merging black holes, providing a new way to probe the universe's most extreme environment. In addition, the development of quantum sensors could enable us to measure the universe's smallest fluctuation, shedding light on the early universe and the fundamental forces that govern space-time. The quest to understand the cosmos is a journey that is far from complete. While the James Webb Space Telescope has provided us with a wealth of knowledge, the road ahead is filled with new technologies and missions that promise to take our understanding of the universe to even greater depth. From the study of dark energy and dark matter to the exploration of exoplanets and the search for life beyond Earth, future missions will build on the discoveries of JWST and bring us closer to answering some of the most profound questions of our existence, from black holes to parallel universes, exploring new frontiers. Black holes, once viewed as mere cosmic anomalies, have become a central topic of fascination and speculation in modern science. These enigmatic objects, with their singularities at the core, challenge our understanding of space-time and the limits of physics. While they have long been thought to simply absorb matter and energy, recent theoretical models have proposed an even more radical possibility. Black holes might be portals to alternate dimensions or parallel universes. This idea, though speculative, opens up new frontiers in the quest to understand the fundamental nature of reality. In this section, we'll explore the hypothesis that black holes might serve as gateways to parallel universes, drawing on cutting-edge theories in physics, and contrast this with traditional cosmological models that view black holes as isolated, terminal objects in the universe. At the heart of the idea that black holes could be portals to alternate dimensions is the concept of wormhole, theoretical passages through space-time that could connect distant parts of the universe or even entirely separate universes. Wormholes, first predicted by Einstein and his colleague Nathan Rosen in the 1930s, are often depicted as shortcuts that could connect different regions of space-time. These structures, also known as Einstein-Rosen bridges, could, in theory, allow for faster-than-light travel or access to other realms of reality, bypassing the immense distances of space. In the case of black holes, the event horizon, the point beyond which nothing can escape, may not be the ultimate boundary it appears to be. Instead of representing a final end for matter, the event horizon could be a doorway to a completely different region of space-time. Some theorists speculate that black holes could act as portals to other universes, potentially linked to the idea of a multiverse, a collection of universes, each with different physical laws, constants, and properties. In this view, black holes are not the cosmic graveyards that traditional models suggest, but rather they could serve as connections between parallel universes, where matter and energy from one universe might be transferred to another. The speculative nature of this theory is based on the fundamental properties of black holes, as described by general relativity and quantum mechanics. General relativity tells us that massive objects like black holes warp the fabric of space-time. At the singularity, the curvature of space-time becomes infinite, leading to conditions where current physics breaks down. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales and introduces the possibility of quantum fluctuations, which could create bubbles of space-time that may connect different regions of the multiverse. Recent theoretical models suggest that black holes could act as conduits for such quantum fluctuations. For example, the idea of a multiverse proposes that our universe is just one of many, each evolving independently, but possibly interacting through quantum effects or black holes. Some physicists believe that black holes, especially those that formed early in the universe's history, could be the portal through which matter from one universe might flow into another, creating new universes as a natural byproduct of black hole activity. In this model, the death of a black hole could, paradoxically, be the birth of a new universe on the other side of the event horizon, perpetuating an eternal cycle of creation. However, these ideas stand in stark contrast to traditional views of the cosmos. In the classical view, black holes are seen as isolated objects that trap everything, including light, within their event horizon. According to this view, once matter or energy crosses the event horizon, it is lost to the black hole. This scenario suggests that black holes are the ultimate endpoint in a star's life cycle, or the end of a galaxy's ability to form new stars. The idea of black holes as portals to other dimensions or universes runs counter to this classical understanding, which holds that nothing escapes from a black hole once it has passed the event horizon. Moreover, traditional cosmology operates within the framework of a single universe, governed by known physical laws, such as the laws of thermodynamics and relativity. These laws have been observed to work consistently within our universe, but the idea of alternate realities or parallel universes introduces a host of unknown variables that challenge our current understanding of the fundamental forces. For instance, the possibility that black holes could connect to different universes suggests that the constants of nature, such as the speed of light, the gravitational constant, or even the nature of time itself, could differ between universes. This would fundamentally alter our understanding of physics, as it implies that the laws governing our universe are not universal after all. Despite the speculative nature of these theories, there are compelling reasons why physicists continue to explore the idea of black holes as portal. Advances in string theory and quantum gravity provide mathematical frameworks that suggest the existence of extra dimensions or alternate realities. These theories, while not yet fully understood or experimentally verified, open the door to possibilities that go far beyond our traditional views of space-time. The idea that black holes might be linked to parallel universes is one of many potential consequences of these theories. The James Webb Space Telescope, JWST, with its unprecedented capabilities in infrared astronomy, may offer the first tangible clues about the nature of black holes and the broader structure of the cosmos. JWST's observations of distant galaxies and the supermassive black holes at their centers could help us learn more about how black holes interact with their surrounding environment. By studying the energy emitted by black holes and the radiation around them, we may be able to detect phenomena that could suggest the existence of wormholes or other dimensional connections. These findings could provide critical insights into the role black holes play in the universe and whether they might indeed be gateways to other realms. The idea that black holes could be portals to parallel universes or alternate dimensions challenges our current understanding of cosmology in profound ways. While these ideas remain speculative, they are rooted in the advanced theories of quantum mechanics and general relativity, which continue to push the boundaries of what we know about space, time, and the nature of the universe. With the advent of JWST and future missions, we may soon have the observational tools to test these bold ideas, expanding our understanding of the cosmos and potentially unlocking new frontiers of exploration in both the physical and metaphysical realms. The role of humanity in understanding the universe's mysteries. The quest to unravel the mysteries of the universe is one of humanity's most profound endeavors. For centuries, we have gazed up at the stars, seeking to understand our place in the cosmos and the fundamental forces that govern it. From the ancient philosophers to modern physicists, the desire to explore the nature of the universe has driven scientific and philosophical thought alike. The study of black holes, galaxies, and the vastness of space not only illuminates the workings of the cosmos, but also raises profound questions about our existence, purpose, and the limits of human understanding. As we make groundbreaking discoveries through advanced technology like the James Webb Space Telescope, JWST, we find ourselves confronting not just the physical mysteries of the universe, but also its deeper existential implication. Black holes, in particular, challenge our understanding of space, time, and reality itself. They're very nature regions of space where gravity is so intense that not even light can escape, forces us to confront the limits of our knowledge. At the heart of a black hole lies the singularity, a point where our current understanding of physics breaks down. This paradoxical region where space-time becomes infinitely curved raises profound questions about the nature of existence and the boundaries of human knowledge. The fact that black holes represent both the most extreme objects in the universe and the places where our theories of gravity and quantum mechanics collide makes them key to understanding not just the universe, but the very fabric of reality. As we push further into the mysteries of black holes, we also confront questions of time and space that challenge our perception of the world. The study of time dilation near black holes, for example, forces us to re-evaluate our concepts of past, present, and future. Time behaves differently near a black hole, slowing down as one approaches the event horizon, offering a glimpse into how space-time can be manipulated by extreme gravity. These findings have far-reaching implications, not only for cosmology, but for the way we understand our own experience of time. The deeper we delve into the nature of black holes and other cosmic phenomena, the more we realize that the universe is far stranger than we can possibly imagine, and our understanding of it is still in its infancy. Yet these discoveries are not just scientific in nature. They also have profound philosophical and existential implications. The more we learn about the universe, the more we are forced to ask deeper questions about our place within it. Are we alone in the universe, or is there life elsewhere in the cosmos? What does it mean to exist in a universe governed by laws that are often beyond human comprehension? As we uncover the mysteries of black holes, galaxies, and the very fabric of space-time, we are confronted with the possibility that our universe may be far more complex and interconnected than we can fathom. Humanity's role in understanding the universe's mysteries is not just that of passive observers. Through scientific discovery, we engage with the cosmos in a way that shapes our identity and worldview. The pursuit of knowledge about black holes, galaxies, and the larger universe is an expression of our innate curiosity and desire to make sense of the world around us. Each discovery, from the first detection of gravitational wave to the observation of distant galaxies through JWST, marks a step forward in our quest to understand the universe's workings. These achievements not only expand our scientific knowledge, but also challenge our assumptions about reality, space, and time. The study of black holes and galaxies also forces us to confront the finite nature of human existence. As we peer into the depths of space, we are reminded that our time in the cosmos is limited. The light we observe from distant galaxies and black holes has traveled billions of years to reach us, and the vastness of space highlights the insignificance of individual human lives in the grand scheme of cosmic history. Yet this realization can also inspire a sense of humility and awe as we recognize the fleeting nature of our existence, while simultaneously celebrating our capacity to understand the universe's most profound mysteries by observing the cosmic events that unfolded long before Earth even existed. We connect ourselves to the larger story of the universe, a story that stretches across unimaginable distances and timescale. The role of humanity in this endeavor becomes ever more significant. Technology such as the JWST is expanding the boundaries of what we can observe and understand, enabling us to explore the most distant reaches of the cosmos. With every discovery, we are forced to reimagine our place in the universe, challenging old assumptions and prompting new questions about the nature of existence itself. These discoveries remind us of both the power and the limits of human knowledge. While we may never fully understand all the mysteries of the universe, the journey of discovery is itself a testament to the indomitable spirit of curiosity that defines humanity. The study of black holes, galaxies, and the cosmos at large is not only a scientific pursuit, but also a deeply philosophical one. It forces us to confront questions about time, space, existence, and the very nature of reality. As we push the boundaries of knowledge through missions like JWST, we are not merely observing the universe, we are engaging with it in a way that shapes our understanding of ourselves and our place in the cosmos. This ongoing quest for knowledge serves as a reminder of the profound mysteries that still lie ahead, and the incredible potential of humanity to uncover the secrets of the universe, the cosmic symphony of time and light. As we journey deeper into the mysteries of the cosmos, we are reminded of the sheer grandeur and complexity of the universe. Each discovery, from the existence of black holes to the farthest galaxies observed by the James Webb Space Telescope, JWST, has brought us closer to understanding the intricate workings of space, time, and light. Yet, the more we uncover, the more we realize how much remains unknown. In this final section, we will tie together the concepts of time, light, and black holes, offering a perspective on the profound interconnectedness of these elements, and leaving you with a sense of awe and wonder at the universe's vastness and complexity. The universe, after all, is a symphony where time and light play melodies that span unimaginable scales, revealing patterns of cosmic harmony and chaos. At the heart of this cosmic symphony is time, the ever-flowing, ever-present backdrop against which all cosmic events unfold. Yet time is not as simple as it might seem. Near black holes, time itself is distorted. The incredible gravity of these objects warps the fabric of space-time, causing time to move more slowly the closer one gets to the event horizon. For an object falling toward a black hole, time would appear to stand still at the event horizon from the perspective of an external observer. This surreal phenomenon challenges our everyday understanding of time and its passage, reminding us that time is not a constant but a fluid and malleable concept governed by the forces of gravity. In the presence of such cosmic giants, time becomes a variable shaped by the curvature of space-time itself. Light, too, plays a central role in this cosmic dance. Light is the messenger of the universe, carrying information across vast distances and across time. The light we observe from distant galaxies, black holes, and stars has traveled billions of years to reach us, allowing us to peer back into the past and witness events that occurred long before Earth came into being. Light, in this sense, becomes a bridge between the past, present, and future, a way for us to connect with the farthest reaches of the cosmos. Yet, just as time bends near black hole, so too does light. The intense gravitational pull of black holes stretches light, shifting its wavelength into the infrared, creating a redshift that allows us to study the farthest corners of the universe. This cosmic redshift is not merely a physical phenomenon, but also a reminder of the expanding universe, where the light from distant galaxies grows increasingly stretched as space itself expands. Light thus serves as both a witness and a participant in the cosmic dance, revealing the secrets of the universe through its journey across time and space. Black holes, those profound mysteries at the heart of galaxies, are key players in this cosmic symphony. They are not just points of destruction, they are complex objects that embody the tension between creation and annihilation. On the one hand, black holes consume matter and energy, pulling them into their singularities. On the other, they are sources of immense energy, influencing the galaxies in which they reside. The interaction between black holes and their host galaxies through processes like feedback, where the energy from black holes can either suppress or trigger star formation, shapes the very structure of the universe. In this sense, black holes are not just the endpoints of cosmic evolution, but also engines of transformation. As the universe continues to evolve, black holes may become the final witnesses to its death, slowly evaporating over unimaginable timescales, but even in their final moments, they will continue to influence the space around them, contributing to the entropy of the cosmos. What is truly awe-inspiring about the study of black holes, light, and time is how interconnected everything is. The vast expanse of the universe, with its galaxies, stars, and black holes, is a web of interconnected phenomena where every event, no matter how small, has a ripple effect across time and space. Every particle of light that reaches us carries with it a story, a piece of the cosmic puzzle. Whether it's the faint glow of an ancient galaxy formed just after the Big Bang, or the distorted light that curves around a black hole, each beam of light provides a window into the universe's history and future. It is through these light signals that we can glimpse the unknown, connecting us to the past and allowing us to peer into the distant future. As we continue to explore the universe, we are not just observing cosmic events from a distance. We are engaging with them, becoming part of the vast, ever-unfolding narrative of the cosmos. The discoveries made by JWST and other telescopes will continue to deepen our understanding, but they will also raise new questions. What lies beyond the event horizon of a black hole? Could black holes truly be portals to parallel universes? How does the interplay of light, time, and gravity shape the future of the universe? These questions drive our curiosity and push the boundaries of our knowledge, but they also remind us of our place in the larger cosmic scheme. In conclusion, the universe is a cosmic symphony, with black holes, light, and time playing central roles in the unfolding drama. The study of these phenomena challenges us to reconsider the very nature of reality, how time and light interact, how black holes shape the fabric of space-time, and how the universe, in all its vastness, continues to evolve. With every discovery, we are reminded that the universe is not just a collection of stars and galaxies. It is a living, breathing entity, constantly changing and revealing new wonders. The more we learn, the more we realize how much we have yet to discover and how much more there is to experience. In the end, our quest to understand the cosmos is not just a scientific pursuit. It is a journey that connects us to the deepest mysteries of existence, invoking awe and wonder at the infinite complexity of the universe.